See if we can make that money.
How does your car look against the rest of those, the rest for those two races? Just pick one where you're best to max it out. We want to max it out at Monza. That's where we're gonna max it out, dude. That's really where it needs to go. All right, fellas, we'll let me save the game and we'll do Monza on the other side of Space News, okay? All right, I'm gonna take a break here. I'll be back around 4, right for Space News. Talk about Blue Origin, what's going on with SLS. Blue Origin had a nasty failure yesterday. Nasty failure. If you haven't seen it, we got Firefly on the 19th. They scrubbed again because of weather. Yeah. We got a lot of different stuff. A lot of different things to talk about. Okay, let me switch this over. I'm gonna go heat up some pizza. I got pizza. I'm gonna heat up the pizza pie. Oh yeah, we also have a potential static fire. That's right. Yep. We also have a potential static fire at Starship. Or at Starbase. So let me get a educational video on for everybody here, and then we'll go from there. No, we don't. No, we don't. No overpressure notice and no road closure. All right, cool. Never mind. Forget I said anything, chat. Forget I said anything.
Discovery, go at throttle up.
Tier 267 from Brimo. 2 more months till... Looking for another educational video here. We'll find something. Can we watch an educational F1 video? Nah. I mean, there's plenty out there, but it's not public domain. All this NASA stuff is public domain, so I can put it on here. I don't have to worry about getting people in my face about it. There's a lot of good stuff in here, but nothing exactly what I'm looking for. You know what? The orbital mechanics one is always a winner. Let's do that. All right, guys. I'll be back momentarily. Enjoy the video.
When ancient man looked to the heavens for guidance from the gods, he noticed star patterns and began to document their movement across the heavens. The ancients believed that the earth was flat, but around 350 BC, Aristotle proved that the earth was round. Later, about 150 AD, Ptolemy presented the geocentric theory, the belief that the earth is stationary at the center of the universe, with the sun, moon, stars, and planets revolving around it in complex orbits. In the 1500s, Nicholas Copernicus of Poland presented the heliocentric theory, the belief that the earth revolves around the sun as it rotates on its axis. This aspect of astronomy evolved into an intricate study of planetary motion known as orbital mechanics. Today, orbital mechanics is applied to space flight and satellites that orbit the Earth or travel beyond our solar system. In the early 1600s, Johann Kepler, a German mathematician, using the data on planetary observations collected by the Danish scientist Tycho Brahe, developed 3 laws of planetary motion. Kepler's first law states,
all planets move in elliptical orbits with the Sun at one focus and the other focus empty.
Applied to Earth satellites, the center of the Earth becomes one focus, with the other focus empty. For circular orbits, the 2 foci coincide. Kepler's second law, the law of areas, states,
the line joining the planet to the Sun sweeps over equal areas in equal time intervals.
When a satellite orbits, the line joining it to the Earth sweeps over equal areas in equal periods of time. If areas 1, 2, and 3 are equal, times 1, 2, and 3 are also equal. Therefore, the speed of the satellite changes depending on its distance from the center of the Earth. Speed is greatest at the point in the orbit closest to the Earth, called perigee, and is slowest at the point farthest from the Earth, called apogee. It is important to note that the orbit followed by a satellite is not dependent on its mass. A large, heavy satellite could be in the same orbit with a small, light one, each sweeping out equal areas in equal periods of time. Kepler's third law, the law of periods, relates the time required for a planet to make one complete trip around the Sun to its mean distance from the Sun.
For any planet, the square of its period of revolution is directly proportional to the cube of its mean distance from the Sun.
Applied to Earth satellites, Kepler's third law explains that the farther a satellite is from the Earth, the longer it will take to complete an orbit, the greater the distance it will travel to complete an orbit, and the slower its average speed will be. Isaac Newton, the father of classical mechanics, laid the groundwork for orbital mechanics. He combined the work of Kepler and others to formulate the law of universal gravitation and the 3 Newtonian laws of motion. While Kepler's laws provided a conceptual model of orbital motion, Newton's laws provided the foundation for the mathematical description of orbits. They explain why a satellite stays in orbit. Newton's law of universal gravitation.
Any two objects in the universe, such as the Earth and the Moon, attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them.
Stated more simply, the more massive the objects are, or the closer they are, the greater the gravitational pull between them. Newton's first law of motion.
A body in motion will keep moving at the same speed and in the same direction unless acted upon by an external force.
A satellite moves in a curved path around the Earth because the Earth's gravitational pull acts as an external force on it. Newton's second law of motion.
If the sum of the forces acting on an object is not zero, the object will have an acceleration proportional to the magnitude and in the direction of the net force.
Newton's second law states that force equals mass times acceleration. It is this mathematical equation and the equation for universal gravitation that forms the basis for calculating orbits. Newton's third law of motion explains how a satellite gets into orbit.
For every action, there is an equal and opposite reaction.
If you blow up a balloon and let it go, the balloon is pushed forward by the action of the air rushing out of it. A rocket's exhaust gases are like the air rushing out of the balloon. The following illustrates how a satellite stays in orbit. If a man stands on a mountain and fires a projectile horizontally, gravity will cause the path of the projectile to curve downward and it will strike the Earth. However, if the man fires the projectile fast enough at a specific speed, the curvature of its path due to gravity will match the curvature of the Earth under it. The projectile will then fall around the Earth, becoming an Earth-orbiting satellite. A projectile fired even faster will have a flight path away from the Earth, but gravity will act to slow the projectile down, change its flight path, and pull it back toward Earth. If the projectile's velocity increased enough, a velocity sufficient to escape the Earth's gravitational pull will be reached. This velocity is known as the escape velocity. It is equal to about 7 miles per second at the Earth's surface. The preceding description did not consider atmospheric drag and the Earth's rotation, both of which will affect the trajectory of the projectile. It illustrated the principles governing a satellite's orbit. There are 6 numbers called the orbital elements, which specify the size, shape, and orientation of an orbit in space, as well as the location of the spacecraft in the orbit. Based on an orbit which is an ellipse, the 6 orbital elements are length of the semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of perigee, time of perigee passage. The major axis of an elliptical orbit is the line joining the perigee and apogee. This line is also referred to as the line of apsides. The first orbital element is the semi-major axis. It is simply 1/2 the major axis. Circular orbits have no apogee or perigee. Therefore, the semi-major axis is simply 1/2 the diameter of the orbit. The semi-major axis is used to define the size of the orbit. From this, the orbital period, or time that it takes for the satellite to complete one orbit, can be calculated. The shape of an orbit is defined by the second orbital element called eccentricity. For all ellipses, the value of eccentricity lies between 0 and 1. The larger the value, the more elliptical the orbit. A spacecraft in Earth orbit with an eccentricity equal to or greater than 1 will escape the Earth's gravitational field. When orienting an orbit in space, a three-dimensional coordinate system must be defined. The coordinate system commonly used is the geocentric equatorial coordinate system, which has its origin at the Earth's center. This coordinate system is a non-rotating reference system in which a satellite's orbital plane tends to remain fixed relative to the stars while the Earth turns beneath it. The XY plane is the Earth's equatorial plane. The positive x-axis points to the vernal equinox. This is the point where the sun appears to cross the Earth's equator on its way north on the first day of spring each year. The z-axis is along the Earth's spin axis toward the North Pole. Nodes are points in a satellite's orbit which intersect the Earth's equatorial plane. The ascending node is the point at which the spacecraft crosses the equator going from south to north. The descending node is where the spacecraft crosses the equator going from north to south. The line joining the two nodes is called the line of nodes. The orientation of an orbit is determined by three orbital element angles. The right ascension of the ascending node is the angle between the x-axis and the ascending node. It is always measured eastward from the direction away from the vernal equinox in the Earth's equatorial plane. The argument of perigee is the angle between the ascending node and the point of perigee. It is measured in the orbital plane in the direction of spacecraft motion. Inclination is the angle between the equatorial plane and the orbital plane. A satellite which has an eastward velocity component at the ascending node has an orbital inclination lying between 0 and 90 degrees. Such an orbit is called a prograde orbit. A satellite which moves due north at the ascending node is in a polar orbit. Polar orbits have an orbital inclination of exactly 90 degrees. A satellite with a westward velocity component at the ascending node is in a retrograde orbit and has an orbital inclination between 90 and 180 degrees. The 5 orbital elements explained thus far describe the size, shape, and orientation of the orbit in space. The final element is a time value used to locate the satellite in its orbit. A satellite moves in a very predictable manner. It stays on schedule. Thus, if the time at which a satellite passes a particular point is known, the time when it will pass any other point can be determined. The particular point chosen is perigee, and the time of perigee passage is the last of the 6 orbital elements. The 6 orbital elements depict a spacecraft's orbit in non-rotating coordinates. To visualize an orbit relative to the rotating Earth, a projection traces the spacecraft's position on the Earth's surface. The projected path is called the ground track. As a satellite orbits the Earth, the ground track shifts westward. There are 2 causes for this. First, the primary contributor is the Earth's rotation toward the east under the orbital plane. Second, because the Earth is not a uniform sphere and bulges at the equator, its gravity is greatest at the equator. This causes the orbital plane to rotate slowly around the Earth's polar axis in a motion called precession. Precession is toward the west for prograde orbits and toward the east for retrograde orbits. For low Earth orbits such as those of the Space Shuttle at 150 miles altitude, the westward shift of the ground track due to the Earth's rotation is about 22.5 degrees, while the shift due to precession is only about a half degree. The inclination of a satellite orbit determines the north and south latitude limits of its ground track. The minimum orbital inclination is equal to the latitude of the launch site and is achieved by launching due east. For example, if a satellite is launched due east out of the Kennedy Space Center, which is located at 28.5 degrees north latitude, its orbital inclination will be 28.5 degrees, and the limits of its ground track will vary between 28.5 degrees north latitude and 28.5 degrees south latitude. If launch azimuth or direction of flight at launch measured eastward from due north is increased from due east, the orbital inclination angle increases as well as the maximum latitude of the north-south ground track. Therefore, the latitude limits of the ground track equal the new launch inclination. Similarly, if launch azimuth is decreased from due east, orbital inclination once again increases as well as the latitude limits of the ground track. The maximum practical inclination from a Kennedy Space Center launch is 57 degrees. This limit is imposed for safety considerations in order to keep the spacecraft and its booster system from flying over land masses during the ascent phase. To obtain an orbit with an inclination greater than 57 degrees, the spacecraft is launched from Vandenberg Air Force Base in California. Vandenberg offers the opportunity for southerly launches with orbit inclinations between approximately 70 degrees prograde through 138 degrees retrograde. A significant advantage of launching from Vandenberg is the capability to economically achieve polar orbits with ground tracks covering all latitudes, from the North Pole to the South Pole. The Earth is constantly turning, and all points on its surface have an eastward velocity, with the greatest velocity occurring at the equator. The farther the launch site is from the equator, or as launch azimuth is increased or decreased from due east, less of the Earth's rotational velocity will be imparted to the launch vehicle. This requires more fuel to get into orbit, or payload weight will have to be decreased. Launches due east from a position on or near the equator, such as the Kourou launch site in French Guiana, used by the European Space Agency, acquire the advantage of a free velocity gain of about 1,500 feet per second. This compares to the approximate 1,300 feet per second gain available at the further north latitude of the Kennedy Space Center. Launching from an equatorial site offers a significant advantage in payload weight capability and minimizes the amount of fuel needed to achieve an equatorial orbit. Since many satellites operate in equatorial orbits, these are important considerations. Spacecraft are launched within a specified time interval called the launch window. Some of the factors affecting the launch window are launch and orbit lighting conditions, sun angles, payload orbit requirements, rendezvous phasing if a rendezvous is planned, tracking and communication requirements, and collision avoidance with other orbiting objects, to name a few. One of the factors defining the launch window for the Space Shuttle is launch lighting conditions, which can be illustrated by plotting time versus day of year. On this plot, we see daylight and darkness at the launch site. The longer daylight hours occur in the middle of the year, summertime. If daylight conditions are required for a convenient emergency landing site for the Space Shuttle, the launch window would now look like this. During the winter months, the available launch window for lighting conditions alone can be as little as 3 hours per day. When combined with the many other launch factors, the launch window becomes even more constrained. The choice of a particular launch vehicle for a mission depends upon the weight and size of the payload and the desired orbit. Expendable rockets used to place spacecraft in orbit usually consist of several stages that may incorporate both solid and liquid propellants for propulsion. When the fuel in each stage is depleted, the spent stage is jettisoned. Staging offers the advantage of discarding weight when it is no longer needed. The Space Shuttle is a two-stage system. At liftoff, the 2 solid rocket boosters and 3 Space Shuttle main engines are all producing thrust. After approximately 2 minutes of flight, at an altitude of 25 miles, the fuel in the solid rocket boosters is depleted and they are jettisoned. The 3 main engines, fueled by liquid oxygen and liquid hydrogen carried in the external tank, continue to burn for several minutes until the shuttle reaches its cutoff velocity. At this time, the main engines are shut down and the external tank is jettisoned. 2 additional burns using the orbiter's maneuvering system referred to as ohms are required to place the orbiter in its final orbit. The OHMS 1 burn occurs about 2 minutes after main engine shutdown and establishes the orbital apogee point. The OHMS 2 burn takes place approximately 30 minutes later and circularizes the orbit. Once satellites are launched and put into orbit, it is often necessary to change the orbit with an on-orbit burn. The common term used in describing on-orbit burns or engine firings is delta V. Delta V is the incremental change in spacecraft velocity measured in feet per second resulting from the burn. The amount of fuel used during a burn depends on the desired delta V change and the mass of the spacecraft. Because the amount of fuel carried is limited, fuel consumption is one of the primary considerations in spacecraft mission planning and is critical to orbit lifetime. On orbit, a spacecraft can thrust in any direction. Burns along the flight path, forward and backward, are the most common. A unique feature of any orbital burn is that if no other burns occur, the spacecraft will later always pass again through the point of burn. Forward burns increase the spacecraft's velocity and are known as posigrade burns. With posigrade burns, the flight path of the vehicle will be raised at all points except the burn point. Burns opposite the direction of flight, which slow the spacecraft down, are called retrograde burns. For retrograde burns, the orbit will be lowered at all points except the burn point. The greater the delta V, the greater the difference between the pre-burn and post-burn orbits. Burns can be combined into maneuver sequences to change orbit size, shape, or orientation. One of the most common maneuver sequences is made up of 2 burns and is used to accomplish an orbit transfer between 2 circular orbits in the same orbital plane. The most energy-efficient transfer between 2 orbits of this type is the Hohmann transfer. The Hohmann transfer is actually 1/2 of an elliptical orbit with its perigee in one of the orbits and its apogee in the other. The burns occur at the perigee and apogee of the transfer orbit. The use of the Hohmann transfer minimizes the delta V required, thus having the advantage of using minimum fuel. The disadvantage of the Hohmann transfer is that it takes longer than most other transfers. The type of the transfer sequence depends on the mission and the amount of fuel available. For example, a space rescue where time is critical might use a fast transfer, while a routine satellite deployment where fuel saved for later use is important would most likely use a Hohmann transfer. The burns discussed so far have all been maneuvers in the original orbital plane and do not affect orbit inclination or node position. There are situations which require an orbital plane change, such as setting up a rendezvous or placing a satellite in an equatorial orbit. To change the inclination, the thrust vector must be directed at an angle to the orbital plane. A thrust with a component that is perpendicular to the orbital plane at either the ascending or descending node will rotate the orbital plane about the line of nodes. A northerly out-of-plane thrust at the ascending node will increase the inclination of a prograde orbit, while a southerly thrust will decrease it. Out-of-plane thrusts require considerable amounts of fuel and are performed only when absolutely required. The Space Shuttle, for example, using all of its onboard propellant, is capable of an on-orbit plane change of less than 3 degrees. Satellite orbital planes and altitudes are determined by their design mission, which very often includes a field of view requirement for optical or communications purposes. The field of view of a satellite is defined as the area of the Earth's surface that is in view from the satellite at any given time. Satellites in high orbits have greater fields of view than those in lower orbits. For example, a satellite at an altitude of 800 nautical miles has a circular field of view with a diameter of about 4,100 nautical miles. A satellite at 200 nautical miles has a circular field of view with a diameter of about 2,000 nautical miles. Low-orbit satellites are often used for photography and other types of Earth observation. A satellite placed in a low-inclination circular orbit at an altitude of about 19,300 nautical miles will have an angular velocity exactly equal to that of the Earth's. The satellite would seem to remain stationary in longitude as viewed from the ground. Such orbits are called geosynchronous and are used to provide a continuous communications capability among any system of ground stations within their field of view. The geosynchronous orbit field of view is constant and is limited to a latitude zone of about 70 degrees north and south of the equator. Effective satellite communications from geosynchronous orbit is not possible at either pole. However, because of their altitude, their field of view covers nearly half the globe. A special type of geosynchronous orbit with an inclination of 0 degrees is called a geostationary orbit. It appears to hover over a fixed point on the Earth's surface at the equator. Most U.S. communication satellites are in geosynchronous orbits, providing near worldwide communications coverage. For effective communications at high latitudes, the Molniya orbit is used. Molniya is the Russian word for lightning and is an orbit used extensively by the Soviet Union for its communication satellites. The Molniya orbit is highly eccentric with an apogee that is near the geosynchronous altitude and an inclination of about 63 degrees. The satellite slows down at apogee in the northern hemisphere and whips through perigee in the southern hemisphere. This provides communications in the northern hemisphere for up to 75% of its orbital period. Several satellites properly spaced in Molniya orbits can provide constant communications at the northern latitudes. Navigation satellites, such as the U.S. Navy's Transit System and the Joint Service Navstar GPS Global Positioning System, use lower orbits so that a user can receive signals from more than one satellite at any time. Another frequently used orbit is known as a sun-synchronous orbit. These take advantage of the precession of the orbital plane caused by the Earth not being a perfect sphere. All sun-synchronous orbits are highly inclined retrograde orbits which precess eastward around the Earth's polar axis at the rate of 1 revolution per year. Since the Earth-Sun line also revolves eastward at the rate of 1 revolution per year, the orbital plane will maintain a constant orientation relative to the Earth-Sun line. If the satellite's period is then synchronized with the rotation of the Earth, it will pass over the same point on the Earth's surface at the same local time at a regular interval. A sun-synchronous satellite ensures that a constant sun angle and uniform lighting exist for the same field of view from pass to pass. Satellites such as those in the Defense Meteorological Satellite Program and Landsat are sun-synchronous, imaging the entire Earth on a regular schedule. The gravitational attraction of the Earth on a spacecraft causes it to move in its orbit around the Earth. There are other, much smaller forces which will cause a spacecraft to deviate from its desired orbit. These forces cause what are known as orbital perturbations. Orbital precession, which is used to obtain sun-synchronous orbits, results from the perturbing effects of the Earth's non-spherical shape. Other perturbing forces are the gravitational pull of the Sun, the Moon, and planets, and solar winds, which are charged streams of protons and electrons that heat the Earth's atmosphere and increase atmospheric drag. In most cases, perturbing forces can be compensated for in the spacecraft and orbit design and present no major problems. If the forces disturb the orbit too much, thrusters can be fired to re-establish its desired orbital orientation or altitude. This is particularly true for spacecraft orbiting at very low altitudes, where the effects of atmospheric drag are greater and, if not compensated for, will eventually cause the spacecraft to deorbit. A spacecraft's operational lifetime is frequently limited only by the amount of fuel available to maintain its desired orbit. When its useful life is complete, a satellite is left in orbit or is deorbited, burning up when re-entering the Earth's atmosphere. When the space shuttle completes its orbital mission, it executes a precise retrograde burn to initiate its controlled return to Earth. This burn occurs nearly halfway around the Earth from the landing site. The new orbit established by the retrograde burn causes the orbiter to enter the Earth's atmosphere about 4,000 miles from the landing site. During the period the orbiter descends from its orbital altitude to atmospheric re-entry, its attitude is maintained by the use of reaction control jets located in the nose and tail of the orbiter. Once the orbiter enters the Earth's atmosphere, its wing and tail aerosurfaces begin to become effective and gradually replace the jets for attitude control. As the orbiter nears the landing field, it maneuvers to a long, straight-in approach at an angle of 17 to 19 degrees. Nearing the runway, it executes a flare maneuver to reduce its sink rate and glides to a touchdown at approximately 230 miles per hour. As the orbiter rolls to a stop, our journey into the world of orbital mechanics comes to an end for now. This is only the basics of orbital mechanics, an intricate study of planetary and satellite motion. The next time you see a launch, you will see it from a different, somewhat knowledgeable perspective. You will understand the fundamentals of spaceflight.
Are you somewhat more knowledgeable? Somewhat, maybe? Are you somewhat? No? Alright, never mind. Just... Oh, Sierra's life habitat. That's cool. Alright, I have all those links. Negative. I am a meat popsicle. Oh, I had that class today. It's just, oh, hey! Snake. You want to see something cool? Here. I learned that the ancients believed that the earth was flat. You are fired! Oh, I'm sorry. No, hey, here. I did a little bit more work on it. Here. Look. Ready? It's right here. Watch. Oh, this is a nice. Very nice. Is that a Supra seat? Yes, it is. Yes, it is. Oh, yeah. Look at that. Oh, yeah. I'm working on this. Made a custom bracket for the Supra seat. It's Supra seat-erific. That's what I've been working on. Also, there's a portal behind me. Pretty cool. Pretty cool. That's what's behind door number 1. Chet, come on down. You're the next contestant on The Price is Wrong, Bobby. Anyway. Is that seat actually from a Supra? Yes. Yes, it is. So that's what's beyond the space. Now you're thinking with portals. That's right. I forget if you mentioned it, but where do you get that? Where'd you get that seat? I bought it. It's from a Supra. No, seriously. It's a Mark II Supra. Here. I will show you. See? Hey, there they are. Oh, I'm not here. See? There it is. Mark II Supra seat in red. Yeah! There's my seat. Right there. Mine's the cloth one, though, so they look like that. It looks like that. They're nice seats. They really are. Pick and pull? Nah, I got it from a friend. That's the seat right there. Yep. It has the... dude, it is super comfy. It's a hugger. The hugger seat. It's actually really nice. It's got the nice lumbar support. It's got angle support. You got the recliner. Dude, I even made the seat tracks work. I re-oiled the thing this morning, and you can adjust the seat. It can go back and forth, which is actually pretty cool. Just like a real Optima What's. Now all we need is a booster and a Supra. Yes. Mm-hmm. Does it have the massage function? No. Dent, what's going on? I just started a job as a drone pilot. All right. Cool. That's pretty neat. All right. Anyway, welcome to Space News, everybody. Let's see what's going on. You know what we're going to lead with? Let me just transfer a couple of links here and there. Yes. Yes, that's good. How much monthly fee would the seat heater be? It's not a BMW, so I don't have to worry about that. Okay. So, we had a pretty eventful day yesterday on the day off here. We will start with that. So, check it out. Yesterday, the NS-23 science mission got ready to launch here, and
New Shepard.
it was basically an eventful mission. Here, I'll show you. I haven't gotten a chance to look at them, Clayton. I didn't see anything pop up in my notifications, man. I'm sorry. I don't know how to tag people on Twitter correctly, but it didn't show up.
T-minus 10, 9.
Watch this, though.
8, 7, 6, 5, 4. Command engine start. 2, 1.
All right, there she goes. Everything looked real good. The takeoff looked fine.
Has cleared the tower and is headed to space. Now you can see on the lower side of your screen that we're gaining speed as New Shepard gains altitude.
So once again,
center.
this footage was from yesterday. Everything seems to be going pretty good here until about, I don't know, about 55 seconds in. Watch. This definitely didn't do what they wanted it to do. I'm pretty sure.
That BE-3 engine throttled up as we're going to push up to max
I'll get more into
Q.
that in a second.
Again, that's the point where
Yeah,
the
right
aerodynamic
around
stress
here.
on the vehicle is at its maximum. We're going to throttle back.
Watch. Up.
And then continue on up to space.
Up. There was an in-flight abort. That booster croaked. Interesting. Definitely a propulsion issue. Yeah, not ideal. Not ideal for a boys at Blue, boys and girls at Blue. There was an abort. The abort looks so unstable. That's actually intentional. It's an intentional thing that happened on the in-flight abort too, which, believe it or not, was with that booster and that capsule. Not a lot of people know that. The in-flight abort test that New Shepard did to qualify it to rate humans on it was with that exact capsule and that exact booster. That was the 9th flight for this booster. I'm not sure if it's had that BE-3 in it the entire time, but that was the 9th flight, and the booster definitely had some problems with that BE-3. The BE-3 definitely didn't he definitely didn't like that. So there's been a lot of speculation as to what happened. It's definitely something with the propulsion, but I don't know. Oof. I think this flame, the next flame here, is pretty damn telling. If we back it up a little ways. So there's clearly some kind of debris here. Something happens right in this area here. If we break it down, I'll show you. Something happens on the right side of the nozzle. Now, keep in mind, this is on the outside of the plume, meaning I don't think it came from inside of the main combustion chamber. Yeah. So something that's very distinctive. I can always say you can pretty much tell what a rocket engine is doing or how well it's working by the color of the flames. The color of flames really do depend. It really depends on what propellants you're using. For instance, if you're using hydrogen, right? The flames should come out clear if you're delivering fuel and oxidizer if you're delivering fuel and oxidizer in the right proportions, right? So like the shuttle engines, for instance. The shuttle engines are hydrolox. The engine is clear. The engine flames are clear. RS-68s, same idea. Now, the RS-68s do run a little bit hydrogen-rich for cooling purposes because they're only using an ablator nozzle. They don't have a regeneratively cooled nozzle, meaning they don't use the propellants to cool the nozzle. The shuttle engine does do that. So the RS-68A's flames tend to be a little bit on the orange side. Now, the BE-3 that's on Blue Origin is what's called a tap-off. That is a tap-off cycle. Now, keep in mind, I was like half asleep yesterday when I covered this, so I really didn't get any of this right. I was like, oh, it's a gas generator. It's not. No, it's not. My explanations yesterday were caca. They were terrible. The BE-3 is a tap-off cycle. So what does that mean? Okay, so BE-3. Let me show you guys a picture of it. Here's a picture of it right off of Blue Origin site. So this is the engine that New Shepard uses right here. Is this the first abort of an operational mission in the U.S.? I think so, Aqualex. Yeah. So, what's going on here? What is this thing doing? So, we have the main combustion chamber down here. See see main combustion chamber. This is where the explosions happen, and then they get shot out the nozzle. Now, if you notice, there's this thing coming off the side of the combustion chamber. Now, that could be... It's kind of hard to tell. It's kind of hard to tell, but somewhere around here, you get fuel and oxidizer into this thing. And then somewhere there's a tap off, basically, on the main combustion chamber. The tap off on the main combustion chamber goes into basically goes around and into the turbine wheels here. So you have a turbine wheel on this side, which is the oxidizer pump, right? And then a turbine wheel over here, which is your hydrogen pump. Basically uses some of the main combustion chamber pressure, a tap off, right? To take some of that pressure and spin turbines.
Discovery, go at throttle.
There's a turbine here. That turbine is attached to a fluid impeller, which is the oxygen turbo pump. And then over here, you have a turbine that's tapping off the engine pressure that's going to a fuel turbo pump. Now, that's basically what a tap off does. From there, the gases get exhausted out basically just a dump pipe here. And from the pumps here, those go basically into the main combustion chamber. You can see one of the pipes, one of the delivery pipes right there, and then it atomizes it, and you get an explosion and it goes out the bottom. But the importance here is the tap-off cycle. It's using turbine, the turbines on the fuel and oxidizer side are using combustion chamber pressure to basically keep spinning. So basically, as long as the rocket engine is on, you could spin these things. Now, why? Why did they go with a tap-off cycle like that? Throttle ability, so New Shepard can land, most likely. Expander cycle engines, tap-off cycle engines like this, they're really easy to throttle. They're really good throttle ability. That's why New Shepard can just kind of come down and land very easily. Sounds exhausting. Yeah. Hey, Foz, 13-month resub. So, that's a much better explanation than what we have here, than what I gave yesterday. Yesterday's explanation sucked, and I'm kind of ashamed of them. I know better than that. So, you have your tap off. Now, if we go back to the footage over here, and we look, some people have speculated that might be the nozzle failing. I don't think it's the nozzle failing. The gases coming out of this thing don't really change shape too much, but it looks like, see, you definitely had something came out of the oxidizer turbo pump exhaust. Something came out. That's what that is right there. That's what that burning up is. And if you notice, right after you get that plume of crap coming out of here, you get a more orange flame, okay? More orange flames. What does that mean? That's how I know it's something on the oxidizer side, because look at the flame color. Go back 10 frames and look at the flames there versus right before it failed. The flames went very orange. So something on the oxidizer side of things was causing some problems there. Now something goes really wrong here. I don't really know what any of this, the rest of this is. That rocket engine is not doing well. Yeah, something is going very, very, very wrong with that. You can see parts coming off the sides, so this could be a turbine machinery failure. In fact, that's what my money's on. A lot of folks have said, "Oh, hey, the nozzle," but no, the flames wouldn't be pushed out like that. They wouldn't be pushed out to the sides if the nozzle wasn't still producing thrust. It wouldn't do that. The expansion, the under expansion on the plume is pretty much the same. Now, once again, we're getting some bright yellow flames here. Now, I don't know what that is. That could be 1,000 different things. Bright yellow would indicate hydrogen. Ooh, something comes off right there. Bright yellow indicates really, really, really fuel-rich hydrogen. So my guess is that something with that LOX turbine went bad. Something over here didn't go right. Either the turbine delaminated itself or it was just put under too much stress, something. But I'm pretty sure it was oxidizer side just because of how the color of the flames coming out. I don't know. I don't know the exact. Hey, Loudon, welcome to Mission Control. You're going throttle up. Yeah, caveman, nice. Fuel turbo pump started to fail, hence the short pulses. I disagree. It's oxidizer side. You wouldn't see flames like that if it wasn't. So the event happens right around the time they say they were throttling down. So wonder if something happened to that throttle down. Well, okay. So Edmund, this is the other part that I didn't really explain well yesterday, okay? The part that I didn't explain well is what's called engine transients, okay? So, engine transients in a tap-off cycle Hydrolox rocket engine will cause problems. Now, or can cause problems is the real right way to say that. So, what is an engine transient? Engine transient basically just means you're changing a lot of things at once. A lot of variables are transient all at once. So, like combustion chamber pressure, flow rate, combustion chamber pressure, flow rate, thrust, specific impulse, all those are changing on the way up. And they definitely change when you throttle the engine. Not so much impulse, not so much that, but you're changing turbine inlet pressures, turbine outlet pressures. You're changing the turbo pump impeller pressures. A lot of stuff change when you throttle the rocket engine. That does stress out components, especially with a tap-off cycle. Now, why? Why would it be with a tap-off cycle more? Well, the tap-off cycle's turbines are taking exhaust right from the engine. They're taking exhaust right from the main combustion chamber. So even a slight change can put stress on the turbine. Now, you got to remember, these things don't have like a rotor brake or something to slow them down. If at any particular point, the pressures coming in from the turbine are basically go faster than the turbine can handle, you're going to get blow by, and that can damage. You're going to blow right by the turbine, and that can damage the turbine. That definitely will break a turbine. So that's if you think of a turbine like a propeller engine on a plane. Propeller engines don't work very well when the air going in is coming in faster than the air going out. That's when they really start to overheat. You really run into problems there because the thing's trying to move the air, and because the pressure going in is the airflow coming in is faster than the airflow going out, they overheat. You're basically going to make a ton of low pressure in front of the prop, or not in front of the prop, kind of in the prop, in the propeller area. The propeller area. No, another terrible explanation on my part. But long story short, you're gonna stress the turbine like really badly. So I don't know if they blew a line. I don't know. And simultaneously, if there's a loss in pressure, then the turbo pump's still kind of spinning. Now, and you could really break something under. Basically, what I'm trying to say is that you could break something under transients. Okay, like I'm not 100% on this, but I know that can happen. You got to remember, like rocket engines don't have a wastegate. They don't have a wastegate. They don't have a blow-off valve. Now, what does that do? In a car, right? The blow-off valve and the wastegate are there to protect the turbine. Because in a car, you're revving the engine, then you're not revving the engine, then you're revving the engine, then you're not revving the engine, then you're revving the engine, and you're not revving the engine, right? You take your foot off the gas, the turbo's still building boost, right? And if you let off the gas and the turbo still tries to put all that boost into the engine, you're either going to A, break the turbo, you're going to overheat the turbine, or B, you're going to blow a head gasket. Because you forced way too much oxidizer in at low revs. And if you get a buildup in pressure on the compressor side with no blow-off valve, then guess what that's going to do? It's going to stress the turbine out. Because that's going to want to make the compressor side spin faster than the turbine side. Because more is going in, less is going out, because the engine revved down, right? So once you're starting to get torsion on the turbine shaft. Same thing can happen with rocket engines, but there's no wastegate. That's what the cars have, a wastegate. They have a valve on both sides of the compressor and the exhaust to alleviate that pressure, to get the turbine to spool kind of quicker, spool kind of more in synchronous with the engine, right? Rocket engines don't have that. They don't have that. If they had a blow-off valve, it'd be very dangerous because the thing would explode. I think this thing made it. I think it made a blow-off valve. I think they stressed the LOX turbine, or some kind of foreign object debris went inside and hit the turbine wheel. Maybe a piece of the combustion chamber went through the taps and hit the turbine blades. This is definitely kind of in line with FOD, with foreign object debris getting into the engine, because something came out of the LOX side of the LOX turbine. Something came out of it, and then the thing started really not working very well after that. So once again, I think it's very consistent with something going wrong with the LOX turbine. Basically this side of the rocket engine over here, but I don't know for sure. I don't know for sure. I'm not an expert on this, but it does seem kind of like it's isolated to this area right here. Could it be dirt? I don't think dirt would be inside of the rocket engine, Clayton, but foreign object debris could be anything. Propeller should move the air. Air shouldn't move the propeller. Midget, that's probably a better way to say that. But yeah, exactly. You can get that can happen here. When you're going to throttle down the engine, for a momentary second, this thing is going to be moving. The compressor's got, or the impeller here is going to want to move faster than the turbine. That does put stress on this design, on both sides of this. For a split second, if you throttle down the rocket engine from a regulator valve over here, your main fuel valve, that's what they use to regulate it. If you're going to regulate that for a split second, the impeller will want to try and spin faster than the turbine. And if the thing breaks or something, or you lose a turbine blade because it's trying to force itself through, yeah, you're going to have some problems. Once again, that happens from changing a lot of things all at once. That happens from transients. And it was throttling through. It was throttling down or throttling up for max Q. I think it's throttle up. On a throttle up like that, yeah, it can cause problems. No, EJ, if it's not exactly what you said, I'm coming back and demanding compensation for being wrong. Appreciate you talking out loud. Helps me think through my own thoughts. Now it's all good, man. Did Blue Origin blow up? Yeah, one of their first stages popped. Yeah, Tessa, or just having no wastegate. I mean, the rocket engine doesn't have a wastegate. There's no wastegate. There's no blow-off valve. You can't have that in a tap-off cycle's design. It wouldn't work right. So the only thing that they have to really make this work is to meter the fuel correctly, and that's why you have that big fuel valve assembly right there. That's the real only thing they need to meter the rocket engine. Did it actually say what happened? No. And Yarg, that's actually a good time to say, we'll probably never know. They won't tell us. I don't think Blue would tell us. They might. It would be cool. That's correct, Hokie. Yep. Mm-hmm. And B3 and New Shepard does throttle down. Yep. But yeah, once again, a throttle down would explain stuff breaking. When you throttle down like that, and if you change the pressure too fast on a rocket engine, you kind of, I'm not going to say you get the equivalent of like compressor stall, but it's kind of like that. Once again, going through transients can break things. But if I had to guess, guys, something went wrong with the LOX turbine wheel. I think the turbine wheel broke. Or something hit the turbine wheel. Something came off somewhere on that engine and found its way into the engine plumbing. Or it could have been in the tank. Who knows? Another thing to note, and I noticed that nobody else is really saying anything about this, and I don't know if this is normal or not. I couldn't tell you. But I did notice something that I've never seen on a New Shepard before. Check that out. I noticed there was a steady stream of liquid coming off the bottom of this thing, if you look. I've never seen a New Shepard do that before. I've watched every launch that they've live streamed. I've watched every single one. I've never seen it do that. So, now, does that mean I know exactly what happened to the motor? No idea. No, I have no idea. I don't even know if that's correlated. That could just be because it was a little colder that day or a little warmer that day than the other times they've launched. It could just be condensation melting off the side of the vehicle. It's possible. But I will say that I've never seen anything like that before. And I don't know if that behavior is well understood. I don't know if they think that's cool or not. I don't know if that caused the problem. Who knows? Watch a T minus 105. You can see more water falling off. It may be related to the upper fill hose. There's no upper fill hose in this design, Darius. It's filled from the bottom. That would be a vent hose up the top. That's a vent line. It's a vent line. More importantly, it is a vent line for hydrogen. Well, you're going to get condensation on the outside, like Tessa. You're going to get condensation on the outside. It's basically, it's water, but I don't know. Brock guy said the vent up top looked like the likely cause of that. Yeah, Tylen, I don't know if that behavior has anything to do with the failure. It probably doesn't, to be 100% honest with you. I've just never seen that before. I've never seen it do that. I've never seen it piss water off the side like that. Never seen that happen. Oh, yeah. Yeah, it's dripping. I see it. Yeah, she's dripping. Nope, nobody was on board. Oh, excuse me. Sorry. Nobody was on board. Everything is okay. No, there's just a bunch of scientific experiments inside of it. But yeah, whatever happened, two things to kind of take a note. I don't think I've ever seen a rocket launch have an escape like this in the U.S. We've never seen anything like that. That's the first thing. Second thing is that shows how really, really well tested New Shepard is. A lot of people think, like I was talking about this yesterday. This is the part of yesterday's kind of conclusions that I think I got pretty much right. It shows there's public perception of what's going on, and then there's the actual engineering. And sometimes those aren't the same thing. If anything, that shows that New Shepard is pretty damn safe. It's one of the safest rockets you could fly on. I guarantee you that. The booster had a catastrophic main propulsion system failure, and if there were people on this, they would have gotten away just fine. Would have been all fine. Everything would have been good. Now, that's kind of at odds with public perception, right? Because everybody looks at this and they say, oh, the rocket failed. A lot of news outlets were praising the launch escape system. Well, that's great. Yeah, Shadow, I did. How many G's do you think we're pulling aboard the capsule? Factor, I have it basically from a person that's flown on New Shepard. Yes, there are people that watch the stream that have flown on New Shepard. Deal with it. It's about 20 G's, but it's only for a second. Still, though, that you'll feel that one later. I'd do it for what it's worth. I would absolutely do that. It'd hurt. It'd hurt. Oh, yeah, you'd feel that later, but it would be the ride of your life. It'd be fun. I read that Blue Origin uses a different vehicle for unmanned versus manned. Is that true? Correct. The RSS H.G. Wells and tail number 3, which is what that first stage was, Linux, are only used for uncrewed science test missions. They are not used to launch people. Another thing that's important to note, two actually other things. That capsule, the H.G. Wells and tail number 3, so first stage 3, were used for the in-flight abort. They were used to qualify the in-flight abort. That capsule has done that already. That capsule did the in-flight abort for Blue, which was crucial to certifying it for moving people on board. Second part, the H.G. Wells and tail number 3 are the life leaders for New Shepard. That booster had flown 8 previous missions. This was its 9th, and the capsule will go on to fly another one sooner rather than later. That is its 9th mission. So it was a life leader. So, whenever, reuse, SpaceX kind of makes it look easy. But, if anything, this shows that it is a difficult thing to figure out. Frankly, I'm amazed that New Shepard hasn't had as many problems as we've seen up until this point, because it's a Hydrolox booster. It is a hydrogen booster. SLS should show you how difficult the hydrogen is to work with, and Blue, frankly, makes it look easy. Once again, it is a testament to that vehicle's design. It's a very safe vehicle. About as safe as you can get for flying into space, even if it is only for a second. Have you seen this from Harry? Is that the pictures of the crash site? If so, yes, I have. Harry posted this. What is he up to? Yep. She kerplunked into the ground. Yep. Can we slow-mo the failure? Ah, Chief, I've done it enough. I've done it enough, dude. If you want to see me slow-mo analyze it, look at yesterday's VOD, or look probably about 15, 20 minutes back. I kind of went through frame by frame. Long story short, something went wrong on the LOX side. I can say that with pretty reasonable confidence. The LOX turbine or the LOX impeller had a problem. The thing switches to running fuel rich, and then after that, it runs way too much in the fuel rich direction and then catastrophically voids itself. The kind of cascading failure here that you're seeing is really consistent with foreign object debris, but I could be wrong. I have no idea, dude. I don't know. You know, until we hear something from Blue, it's all kind of guessing. I'm still guessing LOX turbine. It seems like the LOX turbine just got stressed out. But, see, another thing to consider, guys. Another thing to consider. The BE3 is a great motor. It's a great motor. We've never seen anything like this from it, ever. Ever. And now that I'm really thinking about it, it's got to be more foreign object debris than anything. Something was different this time. What was different? What did you do different? This tells me that it could be process. It could be process-oriented. Something, you know, because other BE3s have launched with much heavier payloads with like 7 people on board, throttled up, and it was no problem. You know, it sounds like something came loose somewhere and got ingested into the turbine. I'm going to put my money on that. If I'm wrong, if we ever hear an explanation, I'll tell you. If it runs fuel rich, it transitions over to engine rich. With hydrogen, Tessa, if it's running engine rich, gaseous hydrogen ends up coming out the bottom. And yeah, we all know how that ends. Yeah. Is this Blue Origin's first ever televised failure? Televised, yes. We've never... There have been New Shepard stages that have not landed in the past. But yeah. It sucks, man. It sucks because I think everybody's going to look at it and be like, no, the rocket isn't safe. But actually, New Shepard's freaking empirically one of the safest things you could fly on. You know? Guess one small piece that came loose after too many uses and they didn't notice. It's not that simple. It's not always that simple, is it, Raiden? I don't know. Yeah. It's hard to say. I mean, a lot of people have been doing like frame by frames and stuff. You know? There's room for a lot of speculation. I did a frame-by-frame picture on the bottom row. You could see some parts falling away. Maybe the nozzle fell apart. Yeah, I don't think it's nozzle side. You're still seeing relatively good chamber pressure right there. I think they sprung a leak on the outside. Look at the flames change color. See what I'm talking about? That's still good. Ooh, see that right there? See how the engine's nice and shiny? When the engine looks like a light, that means it's working correctly. But it definitely flames out there for a second, indicating a drop in combustion chamber pressure. And then it kind of comes back. But it looks like when it came back, it broke somewhere else. Once again, this is a catastrophic failure with the plumbing. It has to be the plumbing. Because you see, like, even right until up until the abort, see the rocket engine is right back to where it was over here. So something... That's FOD. It's gotta be. It's gotta be FOD. Something broke something on there. Yeah, see the flames? Interesting. You see how the engine, it's definitely coming out the left side after. One could have affected the other. Either that or they lost the main fuel regulator valve could have broken. Who knows? If it got stuck or something, I don't know. There's a lot of different things that could be, but I've heard a lot of people message me and they're like, "Oh, it's the nozzle. The nozzle came off." I'm like, why would flames be coming out the side if the nozzle came off? Non-uniform flames, you know? I don't know. Why did the capsule not abort at the start of the engine sputtering? It did? I mean, Jax, I think you're drastically misjudging how quickly this stuff can go wrong. Watch. It was less than a half second before those flames started coming out and the capsule goes off. It's very quick. If you mean like why doesn't it do anything right there? When the first thing kind of pops out the side, see, look at that. Look at the flames change color. See what I'm talking about? Whatever caused this problem is coming out the bottom of the rocket engine right there. Whatever caused that problem it popped out right there. And this is a cascading failure, dude. I mean, something broke right there, and whatever broke, it still kind of kept working more or less the same way. Yeah, see? Look at how orange the flames are getting right there. See how orange the flames are getting? Loss of oxidizer. See, look at that. I'm telling you, you can tell how healthy a rocket is by the color of the flames coming out. Hydrogen should be clear. It should be clear as day. That's bright orange. Fuel rich. Oxidizer. That means the oxidizer lost it. The oxidizer pump took a dump. Oxidizer pump took a dump. Yeah, that's the right thing. Okay, Novus. Yeah, it seems like the thing's still kind of going right, but whatever caused that hiccup there, Jax, causes this next thing. If you're getting differential RPM between the hydrogen turbo pump and the oxygen turbo pump, and they definitely did because it's running fuel rich, very fuel rich right there for a hydrogen motor. You're gonna start screwing with things. Temperatures are gonna go out of nominal ranges. Pressures will start dropping in certain spots. And you're basically dry firing the LOX turbo pump at this point. Yeah, see, something let up. Something couldn't do it no more. Look, it's kind of interesting that the flames came out of the side that we saw sputtering, right? Something came out of the right side of the vehicle, and then their initial failure, after the initial failure, you get another sputter out of that side, right? Now, see, once again, those flames are yellow. Yellow is a lower temperature than orange with hydrogen. Lower temperature. Meaning hydrogen is spilling out somewhere now. That could be getting unburnt hydrogen out the nozzle. That frame would kind of suggest that. Yeah, look, both sides. See, flames out of both sides. Pretty much, Yarg. Yeah, that's a cascading failure. Absolutely. And you got to remember, dude, there's so... A turbine failure on a rocket motor can cause so many problems. And it can cause problems in places you would never guess. So the big explosion that made the vehicle abort came from the hydrogen side of things, right? But it started with the LOX turbine. I'm pretty dang sure because the flames went orange. They went orange. Once again, that means you're running fuel rich out the nozzle, which meaning indicating a loss of oxidizer pressure. Now, you're not gonna, if they lost a piece of the impeller, right? So what's on the LOX side of things, right? You have the impeller and you have the turbine that's coming from the tap off. So if they lost something from the impeller, you'd see that debris come right out the nozzle, or it would get stuck in the injector and then you're screwed. I mean, if it gets up against the injector plate and jams it, the rocket engine will basically explode because you're screwing with the mixture, right? So they didn't abort off the hiccup, but rather the side effects of the hiccup. Whatever their range that triggers an abort violation, Jax, is, yeah, something, yeah, exactly. I think it was the rocket tilting off to the side, and that's what it registered there. It really depends on what their nominal window is for, or what their window is for nominal operation. The thing tilted too far to the side, and the capsule left because they had a weird loss of thrust. But yeah, Yarg, basically, that's what I think. I think the LOX turbine, I mean, it's not the impeller because it would have gotten stuck in the injector plate. The turbine has an open cycle. If you lose a turbine blade or something hits the turbine blade and it shatters part of it, it's going to turn, you know, it's going to turn your angular momentum into precession, right? That means the turbine will start reciprocating like this. And yeah, that's gonna cause that will cause problems. That's what I think happened. Yeah, you see those bird strike videos where they shoot debris into a jet engine and it starts weeble wobbling itself around and then it just blows up. Basically that. I mean, yeah, if the turbine basically cracked and then it voided itself and then blew the tap line, which it could have, like it could have shot through the tap line or something. I mean, I don't know. I could be talking out of my tail. Have we ruled out ULA sniper? Yes, we have. It doesn't look like straight down here. It looks like it was spiraling. Yeah, I mean, there's a lot of things that can happen here, but I think the LOX turbine caused the thing to run fuel rich, and you know, that led to a complete failure on the LOX turbine. And if the LOX turbine failed or delaminated itself or popped, right, it's going to screw with the entire tap-off cycle. And that's going to cause the hydrogen side to go all wonky. Oof. Yeah, something popped out. Something popped out the side there. I still don't think it's the nozzle, once again, because you have flames expanding here. These flames wouldn't be expanding. It would be more straight down if there wasn't still gas coming out of the nozzle. That's definitely coming out of the side of the nozzle. Where I'm having trouble is how the LOX turbine is going to screw with the hydrogen turbine. It might have to do with the tap. It depends on how the tap-off cycle on the B3 works. Some engines tap the main combustion chamber pressure into the hydrogen turbine and then go to the LOX turbine off of the hydrogen turbine. Or it could split, or you could have a regulator valve. There's a bunch of different ways to do it. And this is where I would probably need Rocket Guy to help me a little bit. But yeah, here, check it out. So now this is a single... That's an open cycle tap. I mean, this is kind of what BE3 is like. BE3 has two turbine wheels. There's a turbine for the fuel pump and a turbine for the oxidizer pump. This is a single turbo. You wouldn't use this with Hydrolox unless you had a geared turbine. That wouldn't work very well. Let's see if we can find a different diagram. Here we go. Let's try this one. Okay. Or let's not. Yeah, that's not going to work too well. So this is a J2S. My boat is on an orbital laser system, took it out. How can an orbital laser, Mexican, that's above the vehicle, presumably in orbit, hit the bottom of the vehicle on the way up? Mirrors. Okay. Okay. Yeah, no, you sold me. Some swamp gas reflected off of Venus or something. A microwave laser. That. Okay. How do you have higher RPM in one of the pumps with a tap-off cycle? How do you have higher RPM? Turbine wheel diameter. Turbine wheel diameter. You could have literally a wider turbine, and they do. Well, not literally. I know they have a wider turbine on the hydrogen side because you have to in order to deliver hydrogen at relatively stoichiometric ratios. You freaking sharks with freaking laser beams on their head? Yeah, see, this is a J2S. This isn't exactly what we're looking for. No, that's not exactly what we need. That's from Timmy right there. Yeah, see, that's a single shaft turbine. That's not what the BE3 uses, but that's really close. Okay, guys, nix the laser. Damn it, Mexican. Why? Why are you doing this? Why are you doing this, you jerk? trying to figure this out. Trying to figure this out right now. What's wrong with you? I'm not bidding. The bidding, it's gone up over $1,000 on the rocket engine style. Damn it, Mythic! You really suck! Shuttle engine doesn't use a tap off either, Tessa. See, the B3 has 2 turbines on it. They're on either side. Yeah, there's really no good diagrams of this, man. Blue Origin tap off. I mean, we just get the picture right there. There are almost 200 people watching that LMTV. Yeah, it isn't because I showed it on stream, is it? Probably had something to do with it. Yeah, see, this is all from Timmy here. I was trying to throw in a Real Geniuses reference. Popcorn. Nah, it's gas generator. No. No. Yeah, see, it's hard. We need to find a way to trace the plumbing on this thing, but it's hard to tell from one angle, you know? Yeah, I don't know. It's hard to say, but either way, I mean, it would be cool if we heard something from Blue, but I don't know. They did show pictures of the failure. They posted it everywhere, which is kind of cool. I do appreciate the transparency. Transparency is key. That's going to be key here. There has to be some transparency when it comes to failures, especially with commercial, just like there is with, like, the NTSB. You know what I mean? They have to figure out why this stuff is doing this. You know, if we want to move spaceflight into the level of safety that airlines are at, there has to be transparency. It's super important. Any plans are using a tablet on-stream demonstrations. On-stream demonstrations of what? Like, you want me to draw a tap-off cycle for you? Yeah, I have tablets. They're just packed up. They're still in boxes. I gotta find it. I'm gonna find where that went. It was too late to hide. They already showed it live. Yeah. Okay, so Novus, what did you want me to see? Oh. Oh, that sucks. This is coming from Dr. C. That's Thomas Serbuchen. He's the head of the Science Mission Directorate. After 6+ years of running the world's leading science program, inspiring millions to dare mighty things, and helping our NASA science team accelerate the speed of exploration and discovery, I've decided to resign my position at NASA this December. Well, that sucks. All right. That means I can't do this impression anymore. That is a very big shame. When Administrator Charlie Bolden interviewed me for my job in the fall of 2016, he started the meeting with a surprising question. Thomas, why would you want this job? You're leaving a tenured position and you may be fired within a few months as the administration changes. I reflected for a moment and answered, because it is better to have an impact on this amazing program for a few months than no impact at all. Good answer. This December, I will resign my position at NASA. About 3 months into the 7th year of the most impactful and the most intense job I've ever had, running the world's leading program, pushing science in and from space, continue accelerating the speed of exploration and discovery, and inspiring millions to dare mighty things. Yeah, that's your damn right. The impression is very good. I've been dialing that in over the past 6 years. It has been a great ride. I resign as the longest continually serving Associate Administrator of Science. This is not a goal Charlie and I had in mind when I started. Frankly, I just tried to do the best job I could and help the science program I always loved, which has been intertwined with my career, from building a part of an instrument as a graduate student to proposing and winning multiple instruments and investigations, and finally to my job as Associate Administrator. I've had a tough time making this decision because I love working with Team NASA Science, and I doubt I will ever have a cooler job after this. There's no other job in the world that would let me work more on exciting missions, or that has the potential to affect scientific discoveries. I'm leaving for two reasons. I believe it is best for NASA, and especially the NASA science community, and I believe it's best for me. After 6+ years, I feel like I've had a chance to implement my best ideas. There are without doubt other great leaders and other amazing ideas that need to be tried. And the scientific community deserves opportunity to get that chance. Most importantly, the state of NASA science program is strong and ready for that change now. I think it's a good time to transition, okay? There's another reason for leadership change that we do not like to talk about. Generally, each of us has weaknesses that also affect our organizations, and these weaknesses tend to weigh more heavy on organizations after a few years. This is why leadership changes are imperative to organizations who seek excellence. Each of us has weakness that also affects our organizations, and these weaknesses tend to weigh more heavy on organizations after a few years. On a personal level, I feel it is time also for a change. No, it's not because I'm not having fun, or because I'm less excited now, or because I've achieved any particular goal, or because bureaucratic forces are wearing me down. Simply, it's because I'm at my best when I learn new skills or gain new leadership experiences. I've achieved the key goals I've set for myself when I took this job, and I will continue to struggle with the ones I'm still struggling with, even if I stayed longer. So, as I get ready for my final months at NASA, I want to tell our team members and partners how much I appreciate them. First and foremost, I'm thinking of our leadership team and NASA Science Mission Directorate. I don't think there have ever been a stronger NASA Science leadership team in my career as a scientist, but I know I am biased. We have an incredible set of talented individuals at headquarters doing hard work for the community each and every day. I wish more people could see the excellence and dedication I experienced for the past years. But NASA's science community extends well beyond that. To other NASA headquarters and centers, to the growing number of industrial and academic partners, to our hardworking colleagues in the White House or on Capitol Hill, and to our international partners, without whom we would not be nearly as good as we are. Thanks to all of you. Exploring the secrets of the universe, searching for life elsewhere, protecting and improvising life on Earth and in space are some of the most important and most impactful goals we can pursue as humans. And learning how to build excellent teams who can create historic missions today and tomorrow continues to be worthy of dedicating our lives to. I will spend a lot of effort recruiting candidates to apply for this most amazing and challenging job, and I hope many of our other friends at NASA will do the same. Until I turn my badge in, I will continue to go with the full speed of freedom in the exciting adventure of space, just like Kennedy said during his famous speech 60 years ago, a motto I've used throughout my time at NASA. Then I will spend a lot more time with dear family and friends who have been my support system and a source of feedback throughout. So, what will I do next? The answer is take a break. I've been notoriously bad at finding a new job while I'm fully dedicated to the present one. Thus, my key goals in early 2023 will be spending time with family and friends, skiing on Utah slopes, and going to the gym. I will also spend time processing what this most amazing job has taught me as a leader and a scientist, and I want to talk to others about it. After some time of focus and reflect, I will find what is next for me. And if I'm lucky, I'll get to work with people who care as much about their work as my colleagues do each and every day. Top-down institutionalized complacency. Interesting. Interesting. Yeah, no, I guess that makes sense, you know? You never want to get comfortable. You never want to get comfortable with what you're doing. Doesn't matter what you're doing. Like streaming, you know? There have been times where I've gotten comfortable with my work and doesn't, you know, you kind of coast a little bit. It definitely happens. Yeah, sometimes, you know, sometimes you just got to change stuff. You just got to change things, even if you're comfortable. You want to go to the next level, you know, you got to change things. Part of the reason why we bought this house, why I bought this garage, because I'm, you know, I could just stream Kerbal every day. It'd be fine. It'd be fine for at least until Kerbal comes out, you know, Kerbal 2 comes out, and then, you know, then we're good. But I don't want to just do that. I want to keep going. I want to, you know, I want to start getting into the hands-on things, right? Like, that's why I bought the shop. That's why I bought this, you know? That, and it's really nice to have a place to work on new cars. That's really good. But, you know, this could lead to better things. I understand what he's saying. That makes perfect sense. If you're comfortable, you're not growing. That's right, Scott. Yeah, it's a good way to say that. Good way to say that, dude. Yeah. He'll find a job real quick, man. He's done a lot of good things. It was him and Jim. Remember, guys, back in 2018, it was him and Jim Bridenstine that decided to put Ingenuity on Perseverance, a freaking helicopter. That was his idea. That was Zerbuchen and Bridenstine's idea. What next level is there for Dr. Z after NASA? I don't think he even knows the answer to that question. Sir, can Blue shot the moon or Mars from where they are? I don't understand what that means, Paul. Hey, Nino, you love Jim. Yeah, I miss Bridenstine, man. NASA needs more of that cavalier attitude. But you gotta be, see, that's the thing, man. Spaceflight is this really, really kind of weird area between being bold, right? Being cavalier about things and really making sure you don't send it too hard. You know what I mean? You can't just be like, send it all the time. It requires a little more subtlety than that. I think Jim found that subtlety very well. He knew what people needed to hear, and he knew what needed to get done to do what he needed to do, if that makes any sense. Hi, what's your goal in life? Your life purpose? What do you want out of life? Well, that's a good question. I would go with, you know, that would take some time to think about, dude. But right off the top of my head, I think, you know, what's your goal in life? My goal is to make a difference. You know what I mean? I think that's the biggest thing. I would be able to depart this world, not on a rocket, you know what I mean? Knowing that I made a difference to help move us forward. You know what I mean? Like, how many people have I inspired to go get into aviation, get into aerospace? That's what I mean. You know, knowing that I contributed, knowing that I helped push us to the next level in some way, shape, or form. It's probably an inconsequential amount, to be honest with you. I mean, how many people watch the stream? But knowing that I helped, knowing that I made a difference is really important to me. You know what I mean? We have to go to that next level. We have, you know, we need a city on the moon. We need a city on Mars. It's kind of imperative for humanity surviving as a species. Even if it's just one it's more than most. Element, that's one of my core kind of things. I try not to bring people down. I try to do the opposite of that. You know what I mean? You pull your freaking weight. And then some. Because if everybody does that, then we all move forward together. You know what I mean? And I mean, I don't know. What do you mean by pulling away? Just be a good person. Don't be a dick. Even though, I mean, once again, you're human, not perfect. But that is the next level. But that is the next level, though, because there's other ways to take humanity to the next level instead of space. Hard disagree, Adorable. Yeah, hard disagree. No, we going to space is something that we need to do. And I know what's coming from people that disagree with me on that. Oh, but we need to fix problems down here. Yep, you're not wrong. We can do both of those things at the same time. We should do both of those things at the same time. But we have to go. We have to go. You have to. We gotta move out into. We gotta move out. We gotta move out to the moon. We gotta move out to Mars. We have to. Like, I get it. Oh, just, you know, what's the point of going to Mars? There's nothing there. Yeah, you don't know that. Could be. I mean, Earth is humanity's cradle, but you can't sit in the cradle. You can't sit in the cradle till you're 35. You understand? Yeah, Steam. That's my big one. Knowing that I made somewhat of a difference. Because even if humans get the next galaxy, the next light year, and they'll just kill each other without kindness and other things in space. Yeah, I get. So what? We're always going to have problems because we're not perfect. If we were perfect, we'd all get along. Nobody gets along. That's fine. You have to take that into account. That's why I say we can do both of those things. You know, you have, you know, but to say that, oh, we're not perfect, so we should never go into space is one of the stupidest things I've ever heard. I hear a lot of people say that, Dreams. It's not a good way of looking at things. That's not that, oh, well, you know, we're never perfect, so we don't deserve to extend out into the stars. That's ridiculous. That's nonsense. That doesn't make any sense. That's the biggest false equivalency I ever heard. Anyway, I mean, that sucks that Dr. Z is leaving, but hey, you did a good job, man. You did a very good job. You know, did a good job. But anyway, guys, before we get too existential, let's move on to the next thing. So here's the next big news. I kind of saw this one coming, but Exploration Ground Systems tweeted this. The NASA Artemis 1 flight around the moon will launch net September 27th with a backup window of October 2nd. Now, NASA had been targeting Friday, the 23rd, but I had a feeling they wouldn't be doing that. The reason why I had a feeling they wouldn't be doing that is because the 23rd is when NASA's DART mission will impact the Didymos asteroid. It's the double asteroid redirect mission. And the reason why, like, okay, so what does that have to do with going to the moon? Well, both of those missions, Artemis 1 and the DART mission, are missions that are going outside of low Earth orbit. The DART mission by a very long way. And DART is set to impact then, and they're not gonna launch SLS at the same time when they need to track Orion out to the moon. The DSN is already being used. It's a range conflict violation, or just a range conflict, not necessarily a violation. So I had a feeling they'd be going on the 27th with a backup of the 2nd on Sunday. Cool. Remember, guys, this is all pending the tanking test that they use to test the hydrogen valve there, and more importantly, it is more about getting a range package approved to be able to certify the vehicle flight termination system, certify that the vehicle flight termination systems are good to fly. Yeah, today I learned the meaning of net. Oh yeah, yep. Do they know if they need to change out the FTS battery packs yet? That's the big one, Jim. No. It does make sense if you look at it through the lens of counter-tribalism, just my theory. Guys, we're imperfect. Someone's always going to disagree. You could give out 100 free lunches and somebody would complain that this isn't the lunch that they want. It's just how it is, dude. The second we understand that, the better. The sooner we understand that, the better. Because then you can learn to compensate for it. You know what I mean? I don't know if you saw or dissociated, but I put together a frame-by-frame analysis on the NS-23 launch failure from yesterday. Oh, we did already discuss it, Vulcan. You missed it by about 15-20 minutes. But yeah, cool. Thought on the new FUV, Ferrari utility vehicle. I'll check that in a moment. Targeting 9/21 for the cryo test. They moved the cryo test to the 21st. Cool. Okay. What date is the testing? So it was the 17th. They moved it to the 21st. 21st, they're going to do testing of the valve. If the valve works, then it's just the flight termination system battery certification. Rumored to start at 400K. All right, alleviate. What is this? What am I looking at here? Suicide doors. Cool.
Discovery, go and throttle up.
Man, all that time and effort, and you made a car that looks like a shoe. Enzo's turning in his grave, I swear to God. It has a V12 though. Why do car designers go for that super thin look these days? I don't know. I hate it. I hate it. I think it looks horrible. The only thing I like about it is really the suicide doors. I like the suicide doors. That's cool. This is... Nope. Nope. That doesn't do anything for me. I also have a couple of questions here. Why did they literally show their car not handling well on the video? So this next shot right here, when it's going around a left-hand corner coming from that villa. Watch. Did you see it? Watch the back end of the car. They literally showed their car not handling well in the promo video. You know why it doesn't handle well? Because it's shaped like a shoe. Look, right there. See it wiggle? You see it? Okay. All right. That's fine. All right. Whatever. Oh, wow. That's great. You get all the things that make Ferraris cool, except worse. Oh. Yeah, of course it has a decent engine. It has a V12 in it. This doesn't do anything for me, dudes. This doesn't do nothing. It looks like a fat Porsche Taycan. Like, ugh. Oh boy, the knob. Another thing I hate BMW for. Porsche Taycan, but it ate too much spaghetti. What are you trying to accomplish with this? That's like what are you trying to do? You know what the messed up part is? I'm sure it's a really nice car. It probably is a really nice car, but it's a really nice car that quite literally looks like every other car designed ever. Enzo's turning in his grave, man. If he realized Ferrari made an SUV, he would freaking blow a gasket. It looks like a Subaru Crosstrek. Like, it looks like a Crosstrek, man! And don't get me wrong, the Crosstrek isn't a bad-looking car, but this is a Ferrari! A Ferrari's not supposed to look like a damn Subaru! I drive a Crosstrek and it looks something like this. Don't diss Subaru like that. Where did I diss Subaru? In what I said, Jax? Get off the outrage train and listen next time. Jesus. Ugh. No, thank you. Nope. Hard no. Yep. If I never see that car ever again, I'll be pretty happy. Yeah. Please tell me you hate the Urus? What is a Urus? Can't wait to see this garbage litter the streets around me. Serious, for once we agree on things. Jeez, it's the Lamborghini's 4x4. It's called a Urus? A Urus. That's an Audi SUV with a Lamborghini logo on it. Give me a frickin' break. Ugh. 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 Oh, God. Not even painting that crock of caca will freaking save it, W. Yeah, Dragon, it's gross. It's gross. It's disgusting. All right. And now, onto something completely different. Here, this is coming from Sierra Space. Let's see if we can get some eye bleach here. Now the questions, you have to own one. I have to own one. What am I going for? Between a Lamborghini Urus or that Ferrari Montgasque or whatever the freaking name of it is, I don't know. If I have to own one, I'll walk. Thank you very much. I'll walk. Yeah, I'd rather walk. Dude, I hate crossover SUVs that much. You know how much a car has to suck to get me to not want to drive the car? American. You know how much it has to suck to say, "No, I'll use my bicycle, thank you very much." No, that's good. You can keep that. Yo, Haas with the raid. Thanks, man. Haas, wait. All right. Hold on. Before we do that, Haas, does this do anything for you? Does that do anything for? That does nothing for me, man. That doesn't do anything for me. Anyway, actually, I don't know if Haas is even here. Cause he was doing the driving school thing today, wasn't he? The Taycan outsold the 911 last year. Gross. Nope, nothing. Okay, all right. Hey, man. All right. What about this? All right. Let's just mute the sound because it's annoying. What about this thing? Does this thing do anything for you? Now, hold on. Here's some pictures of people. It's just... Dude, I hate it. I'm sorry. You know, I know you're not, I know you're not supposed to hate anything in this day. I hate it. I can't stand it. Anyway, you know what? Let's talk about fun driving. Haas, how's the driving school? I saw you learning about weight transfer. That was pretty cool. How did it go? It fits Enzo's goal of selling anything to fund the race team. You know what, Mac? I never thought about it like that. C3 Corvette is the best car. Mm-hmm. Yeah. This. What is this? What is this? Something that I don't care about? Oh, no. Yeah, that's cool. I like that, Doom. Yeah, that's pretty neat. Hey, Ensign, what's going on? Anyway, welcome, Haas Raiders. How you doing? It's cool. Haas is doing a driving school on stream. He's Haas partnered with what is it? It's BMW Motorsports, right? To basically stream learning how to race, which is actually really cool. Polaris Space News, if it wasn't already linked. Yeah, I'll check that in a moment. But anyway, guys, if you guys want to see Haas learn how to wheel a BMW, what is it, an M4 GT? Go give him a follow. Trust me, you'll like it. That Hyundai Inline is so 80s in a good way. I think it looks great. Somebody's actually doing something different, even though it's just an 80s car. Hey, Lucino, what's up? I'm on a trip in Germany. Yesterday, I went to the Speyer Museum, and today, Sinsheim. Amazing places, lots of cool cars, planes, vehicles of all kind, like space shuttles. Yep. Anyway, Haas, yeah, I'll see you, buddy. I thought you hated BMW now. Not really that big of a fan, but yeah. Explosive, 33-month resub. You didn't share the vid I sent you on stream, did you? Might have to save it for after hours. That's not going on stream. Core Space posted this video, some cool stuff to actually talk about. Pulse detonation engine. Isn't it a RDE? That's a rotating detonation. Yeah, I know. It got buried. All right. Anyway, let's check out the next bit of space news, guys. So if you're coming in from Haas's stream, I'm EJ. I do space stuff. We're talking about space news right now. This is coming from Sierra Space. Let's see what we got.
This burst test is what's called a UBP. It's an ultimate burst pressure test. And the reason we say ultimate is because we want to bring it to failure. I'm Sean Buckley, Chief Engineer of Life and Node at Sierra Space. Life Habitat is an inflatable system which is made of a series of soft goods layers. And those soft goods layers, under pressure, deploy to an expandable volume that you can use in space. In preparing the article, there are several things that we want to do. And in that preparation, we take a look at the exterior of the article. We make sure that all the elements are cohesively working with each other. We make sure that the area around the article is going to provide us with the data we want from the test. If we want to keep expanding and we want to keep moving.
Was that guy hammering in a bolt? Okay.
To new reaches and new heights. We have to embrace technologies that we're not comfortable with. Soft goods is one of those. And soft goods for habitation is a game changer.
LIFE stands for Large Integrated Flexible Environment. It's an inflatable habitat. It's very flexible when it's not
SLS or
pressurized.
Starship,
Once
Hizzle.
it's pressurized,
New to the channel?
it is like a
You like the
rock,
name?
and it's stronger than steel.
Say
5
some
times
rocket
stronger
review,
than
man.
Steel. The idea is it launches in a packed state, and then when you get on orbit, you inflate it so you have more volume and you have more room to live, work, and function. Hi, I'm Gerard Valle, and I'm the Structures, Mechanisms, and Soft Good Lead for Sierra Space Life Habitat.
Cool.
We're really just testing the structural restraint layer, which is what carries the load, and it's 1/3 the size of a life habitat.
So the restraint layer is made up of a material called Vectran. Vectran is an extremely high-strength material, performs really well in this application. It gets us the best performance while maximizing the livable volume inside
No,
the
dude, I
habitat.
haven't.
My name is James Kerwin, and I'm the Program Manager for Habitats at ILC Dover. Years of research have gone into perfecting how it's woven together, how it's sewn together.
Cool.
What this test is demonstrating is that we can achieve a higher factor of safety requirement than even hard structures can.
There's a lot of preparation in order to get the module prepared for test. So right now we're doing a low pressurization. We'll bring it up to a low pressure. A team will go out there, they'll take a look at the system, make sure the architecture looks good, and then we'll start to ramp it up. Take a couple hours for us to get there.
So the goal is 180 PSI or larger. I'm looking forward to the day playing out. And the more margin you get, the further ahead we are. If we don't get to 180 PSI, it's a step backwards. So getting to that first gate is important, and then progressing from there.
This test is important because running models and analyses can only give you theoretical results. You need the hard data to back up the research that we've been doing.
So we have a set of high-speed cameras, and the high-speed cameras are what will capture the actual event. With the high-speed, you'll be able to see exactly where the failure initiated, as it usually starts in one location, propagates throughout the whole test article.
Oof. Okay. All right.
Great day for
It
the
exploded.
program, great day for ILC, for NASA, our partners, and Sierra Space.
You can design and analyze something, but you don't really know until you run a test. And typically you test beyond the design capability.
Oh, the clever free. Wow, look at that.
I think we're at an inflection point where the technology is about to be kicked off and utilized, so very excited about the next steps coming up.
The
That
seam
was
is
a
right
lot
up here.
of force,
The
man.
seam is typically the weakest point in the design. So for it to have not failed at the seam is very interesting. And it goes back to wanting to see the high-speed footage and finding out what ultimately caused this.
This is a highly successful test. Our expectations were to meet and exceed the 182.4 PSI, and we burst at 192, which was incredible for us.
Nice.
Pretty amazing.
Hang on. I want to watch that again. $192, $154. They were returned to NASA, Christian. Huh. Interesting. The initial pop was over there. See it? It didn't, yeah, it didn't fail exactly on the seam. Interesting. The whole Bigelow company went to NASA or just Beam? No, all the assets were transferred to NASA. All the assets that NASA had patents on. So like the HAB module designs, TransHab, that was they moved the patents back to NASA and the hardware, whatever hardware they had left. Yeah, it looks like the mounting area, not the fabric itself. I mean, yeah, there's. I mean, you're never. What's 192 psi? 192 psi is. It's very up there. 192 divided by 15. 13. It's 13 bar. Yeah, you're never, ever, ever going to see that hab module or any hab module like that inflated to 13 bar. If it's at 13 bar, something has gone catastrophically wrong. So that's a really, really high... Hang on a second. You're never, it's never, yeah, that's a 13, yeah, 13 factors of safety, which is good. I mean, that's good enough, Rocket, right? That's really good. You're never gonna exceed that. Oof. Yeah, no, it's, yeah, that the guy, one of the engineers said that. You'd think it would fail right at the seam. It didn't. It popped over here. Not only did it pop over there, but it was non-uniform. You see that? It didn't fail continuously. It unzipped. And then from there, it came undone right there. That's a very weird result, to be honest with you. I would do this again. That's a very interesting... I mean, the engineer said it right in the words. He's like, it's very interesting that it didn't fail on the seam. That's where I thought it was going to fail. That's not ideally what you want to hear when you're doing a failure mode test like this, but either way, pretty cool. How much of a difference does it make being up there versus down here? What do you mean, goalie? How much of a, what do you mean, how much of a difference? I don't understand. I mean, typically when a cylinder fails, it'll fail in the direction of axis. This failed along the circumference. Yeah. It's very strange. Very strange, Novus. Yeah. I mean, okay. So with something like this, it's about pressure. It's about pressure differential. So that thing was inflated to 9 bar, right? Or no, 13 bar is what we said. It's 1 bar outside and 13 on the inside, which means that if you were testing it up in space, it would fail at 12 bar internal pressure, because that is the total delta between ambient pressure up in space, which is nothing. It's vacuum, there's nothing. And the internal pressure. So it would fail at 12 bar in space. So 1 bar is the difference, because space has no pressure and we're at 1 atmospheric pressure down here. So 1 bar is the difference. I mean, wouldn't it be 13 above ambient? It depends. It really depends. It depends on it depends on what their internal PSI gauges were. If they were using PSII or PSIA, that's it really depends. This is the future. What is this? What is this? Self-assembling space architecture. Oh. Yeah, that's kind of cool. That's pretty neat. If you guys want to see it here. Anyway, cool video from Sierra Space. We do seem to be seeing a lot more of what they're doing lately, which is actually pretty rad. Here. Oh. What does this do? Canyon cubes? Why is there a Falcon 9 on Mars? That's a lot of things that can go wrong, man. Tell you that right now. That's a lot of things that can go wrong. Now, don't get me wrong. That video is from MIT. It's from MIT Space Exploration Initiative. So if they think it's right, I'm inclined to believe that they're probably correct. But man, looking at this from a straight SE standpoint, that's a lot of things that can fail. That's a lot of things that can fail. What if the mechanism jams right there? Then you're screwed. Yeah, Rocket Guy, I'm not... This is a little... I get it. They're trying to take Starlink, do what kind of like what Starlink does, but I get I don't want to do okay. That's a lot of stuff that can fail, man. They've been working on this at MIT for a few years. Recently, the lady running it was on Lex Friedman. Oh, cool. Yeah, there's a lot of things that can go wrong, man. That's a lot of single fault redundant architecture that I'm looking at here. But hey, like I said, it's MIT, so I you know, like you gotta take that perspective into account. I'm pretty sure that people at MIT know a little bit more about rocket science than we do. You know what I'm saying? Inflatable modules would do that easier and safer. I agree, LM. Yeah, I agree. That seems like and once again, I don't know anything about the project, so I'm gonna just go with it could work. Sure, why not? But you know, here's the thing. It's really easy to doubt ideas when you look at them from the outside in, like what we're doing. So, you know, trying to get out of a habit of doing that. That's a lot of stuff that can go. With that being said, there's a lot of stuff that can go wrong there. There's a lot of things that can go wrong there. Space is stored in the balls. Yes. You just buy it. That's Bostonian. So you're telling me that we shouldn't put our faith in, you know, in the institution that designed the guidance system that landed people on the moon? No. Yeah, no, I'm just biased though, right, Squish? I know you're kidding, but also, piss off. You like apples? I got a number. How do you like them apples? Anyway, interesting idea. They made synths, though. No, they didn't. It's about cargo volume and weight and can be reconfigured to any needed arrangement or expanded. I understand that, Doom, but... Okay, alright. Not trying to be a SpaceX fanboy. Starship can literally do anything that thing can do, and it can actually go places. Why would I do that over Starship? Question? Applesauce. Beach. Yeah, that's right. You could send 10 of those things and make a giant room. You could literally, I mean, I guess, Yarg, for a mission that's like 30 times more complicated than just sending 10 starships. That is a much more complicated version of this, and this has been in development for so long. I don't know, man. It just seems like there's a lot of things that can go wrong there. there's a lot of single fault redundancies in this design, meaning that if one thing goes wrong, the whole thing goes wrong. What if one of the modules breaks during deploy? Then you don't make a perfect cube, and then you're screwed. Unless they're launching out extras right there, right? Like, and don't get me wrong, that's not like that's too hard to do. You know, it's interesting. Interesting. James Webb had 340 single point failures, and it was fine, Kappa. Yeah. Yeah. Right? Space stations. Can 10 starships dock together and turn into a space station? They could. Sure, why not? There's a radial docking port on it, man. Of course it could. Just string a freaking nice chain of them together. Hey, Simulated, what's going on? Here is the RFA update. Rocket Factory Augsburg. They've officially signed a contract under ESA's Boost program. After winning the DLR Space Agency micro launcher competition, the prize money of 11 million euros will now be implemented through this program. Cool. Good for RFA. Nice. Who's the fanboy now? Are you drunk? Are you drunk? Are you listening to yourself right now? A little early to be boozing, don't you think?
Discovery, go at throttle up.
Yeah, that kind of makes sense. Yep. I don't know, it's past 5 p.m. Never too early. I guess so. I guess so. Damn. No such thing as too early. Chat, you might have a problem. Never too early when you're retired, but it's afternoon nap time. Been jobbing on 3D printing all day. That's cool, dude. Right on. It's 5 o'clock somewhere. It's 5 o'clock here. Damn it. Check your DMs. Nah, I don't want it, Sawyer. I don't like you. I mean, hi. Yeah, all right, what's up? Oh, boy. I have a lot. Okay. Oh. Cool. Sorry, I'll give that guy a follow. A lot of DMs there. Jesus. Okay. See last, please. Oh. All right. If you could theoretically crunch up the mass of a fully fueled Falcon 9 into a starship's cargo bay, would it be able to launch that to Mars or even into orbit? Yeah, I was just checking next launch, dude. Yeah, you got about 4 hours, pal. Squish, what did you say again? Hold on. If you could theoretically crunch up the mass of a fully fueled Falcon 9 into Starship's cargo bay, would it be able to launch that to Mars or even to orbit? So, Squish, you want the depot starship. You want a depot starship. Yeah, maybe. I don't know. I mean, a depot starship? Sure. Yeah, I could do it. If you could just, like, kind of weasel a Falcon 9's fairing onto the front of a depot starship, yeah, that should be enough. That's just napkin math, though. What's Depot Starship, guys? It's an extended version of Starship where the payload bay is just filled with fuel. Considering a fully fueled Falcon 9 is 550 metric tons, that's a no. Not even with the depot? Depot Starship rocket guy, it's close. Closer than you might think. I mean, Falcon 9's first stage, provided we can air start, you know, all the engines, right? Yeah, if you're just playing it Kerbal style, where you could just turn engines on and turn engines off willy-nilly, right? You could use the first stage to... And boil off wasn't a thing, right? Like, you could definitely... Yeah, you could do it. The Delta V is there. I mean, Depot's carrying a lot of fuel, man. Starship only has 150 metric ton capacity. I'm talking about Depot Starship, dude. Depot Starship is a starship where the payload, it's extended, and the payload bay is just full of fuel. It's an extended starship. It's like a super heavy-sized starship with, yeah. Yeah. Depot Starship. And provided you could, like, refuel the Depot Starship on orbit and then attach a Falcon 9 to the front, I guess, it's possible. That's a lot of Delta V. But that's taking, you know, obviously we're kind of basing it off of, like, boil off not being a thing, air startability and restartability on engines not being a thing. There's a lot of things that we're kind of just being like, yeah, no, that's not a thing. You know? Anyway, let's see what's going on. What do we have for launches? So, we have a Starlink launch tonight. Hell yeah. I guess I just don't understand the question since Depot has no carrier capacity. We should basically ask if we could glue a fully fueled Falcon 9 to the front of a Depot Starship. More or less like that. I mean, yeah, crunching it into the payload bay would not work, Rocket Guy. That was the beginning of the question. I said, no, we wouldn't want to do that. You'd take Depot Starship and attach a whole Falcon 9 to the front of it. I don't know how you'd do that, but whatever. We're already way off in La La Land there with that analogy anyway, or that mission kind of... mission requirement, so yeah, who knows. All right, so this is coming from Next Space Flight here. What do we got? We got a Starlink. We got Starlink 434 going out of Slick 40 at 1010. Then it's an issue with thrust. Yeah. Speaking of Starship, super heavy Starship, heavy Super Falcon 10. All right, let's see what we got. All right, guys, I'm done with the theoreticals. Let's go back to snap back to reality. Oh, there goes gravity because your thrust is higher than the 1.0. Lose yourself in the orbit. You never let it go. You only get one moonshot. Do not miss your chance to burn. All right, anyway. See? Now I have your attention. All right, cool. So this is coming from Zach. What's Zach up to? The 33 engine booster startup sequence appears to involve 16 different engine groups. After the center engines ignite, the remainder spin up 2 at a time, opposite pairs until 33 are lit. This is based off the observations made during the spin prime test. Yeah, that's what I said too. It's a sequenced ignition. So this is Ryan Hansen's space. This is his animation that Zach posted here. So, yep, there you go. Cool. You want to know how the startup sequence? This is why they call, like when rockets get ready to launch, they call it a sequencer, because it's sequencing events, like engine starts, for instance. That was bad, and you should feel bad. And yeah, you loved it. Yeah, it's like a millisecond staggering, Rocket Guy. Crazy, right? Dude, the fact that you can zing 3 of them at the same time and it doesn't break anything is pretty impressive. How quick is that in real life? Oh, yeah, you want to see how quickly it happens? Here you go. Oh. Let me get over to the NSF footage. Give me 1 second. NSF will have it. I'm trying to figure out which one it is. Sorry. Trying to figure out which one it is here. I think this is the spin prime here. Nope. You got it, Phil? Go. So you want to see how fast this happens here? Back it up. Ready? Once again, it's coming from NSF Live here. Or Starbase Live, I should say. Ready? This is how quickly that happens. About that fast. So I'll tell you when all the engines are on. Ready? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yep. Yeah, I couldn't even count fast enough. That's how fast it comes at you. About less than a second. Less than a second, basically. Hey, roundabout. I want to see it with fire. Soon. Don't we all? Starting grid 1. We have 1 engine ignition. We have 2 engine ignition. We going to 2, going to 3, going to 3, going to 3, going to 4. We have 4 engine ignition. We have 4 engine going to 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20 engine ignition. 20 engine ignition. 20 engine ignition. We go for 33. 20 engine ignition. Go for 33. Go for 33. We're going once, going twice. Sold for 33 engine ignitions. Ow. I don't want to do that again. You're good at it? Thank you. I'm not very good at that, man. All right, so Greg Scott took these pictures here. These arrived at the SpaceX dock at Port Canaveral recently and were unloaded. What did Greg take a picture of? Oh, Starship stands. Ooh. A 1 Starship stand. A 2 Starship stand. A 3 Starship stand. Cool. Once again, Greg Scott took these pictures. Oh, that's a big trailer. Man, those things are heavy. Look at the dude. That is a heavy boy trailer. We're not talking fifth wheel here. We got fifth wheel, sixth wheel, and seventh wheel right there. Seventh wheel. Yeah. What kind of truck is it? Kenworth? That's a sweet freaking truck, dude. How many wheels you want? Yes. Yes. That was good. You need to put it up at the local sale barn auction. Ain't no sale barn auction around here, man. I live in Massachusetts. Dude, if I went around and asked somebody where the local stockyard is, they're going to look at me funny. Okay? Ain't no stockyards around here. We got trucks. No farmers? You'd have to go out to Western Mass, dude. There's no there ain't no stockyards around here, not that I know of. Can we tweet Elon to get a SpaceX mission for spin tires transporting rocket parts? That'd be cool, else wouldn't it? Any info on who is leasing the high bay from NASA? I've heard nothing, Hibbit. I want it to be Starship because I want to see a Starship get assembled inside of the VAB just for old time's sake, but I don't think that's gonna happen. Anyway, Starship transport stands down to the Cape. Very interesting. Let's see. Speaking of that, let's see if there's a new NSF video. Let's take a look-see. So we saw OLM upgrades. We saw the Wayne Hale special, which was one of my favorite NSF lives. Space cows watch Raptor engines explode. Oh. All right. We'll roll with it. This is McGregor Live cameras here. You're a baby trailer goalie. Got him. I love how the cow straight up just doesn't care. Now it's just like... Look at that. Look at the calf over there. The calf is like, huh? Calf's like, ah. Alright. That happens all the time. Oh! 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 Does that mean it's not coming on then? Oh! Rocket, that was very abrupt. Damn! Me after Taco Bell. That looked okay. I know. Hard start. Oh, that's, yep, that's a hard start. Yep, yeah, that's, that didn't end well at all. If the rocket engine makes a burping noise, yeah, I'm pretty sure something went wrong. How much you bet they are testing even higher chamber pressures? I know for a fact that that's what they're doing, Lulz, if that's any consolation, so, yeah. Seems okay. It's pretty cool, Creeper, yeah. Sweet. Yeah, the rocket, that roundabout, the rocket took a dump. Took a dump. Oh! You can hear the carnage. Oh. 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 Nope. 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 All right, I'm going to play it one more time. Yeah, Rock Guy, definitely a hard start. Definitely a hard start. That's just... Oh, that's hard to listen to. Oh, it voided itself pretty quick. Yeah, you can hear the, crap. What does hard start mean? Like, and don't do this, but hard starting a rocket engine is basically the equivalent of putting your foot to the floor on the gas pedal and turning the starter key. Yeah, on a car. Yeah, it might be fine. It's probably not going to be fine, though. It's probably not. That's probably not going to work how you want. Yeah. 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 I mean, we could sit here and try and figure out what it did, but I'll tell you, it's a hard start, but I don't know what it is. It could be a bunch of different things. I mean, I'd have to see the rocket engine to tell. You hate that noise. Should I stop doing that? No, you're good, Chimp. Just keep doing it. Oh, there we go. Looking good. That's not looking good. Well, I'll tell you what, that was a shutdown. That Raptor didn't break. Whatever that was, that one didn't break. It just coughed a little bit. Yeah. Rocky guy, LOX pressure, right? LOX pressure. Look at all the methane burning off after that. No, you didn't lose fuel pressure. There's plenty of fuel there. This is the latest with the Florida Cape updates from NSF. Oh, sweet. Oh, okay, cool. Yeah, I got you, Darius. Yeah. Ooh. Ooh. Yeah, Farm, there's plenty of fuel. Oh, there's plenty of fuel there. That looks like a shutdown. That looks like the computer shut it off. With whatever they were trying to test, the computer said, nope. The computer caught it before the thing completely failed. Because they shut it, and when they cut it, a bunch of fuel sprayed out, residual sprayed out. That does happen. That happens with rocket engines. It's like if you're running the sprinkler in your front yard and you turn the hose, you turn the hose shut, and the sprinkler it doesn't shut off instantly. There's still a little bit of residual. Rocket engines do the same thing, but it's with explosive fuel. So you tend to get a little bit of fire coming out the bottom. Better to test it and break it on the ground. Neil Armstrong said you got to fail down here so you don't fail up there. Yep, see? Dude, look at that. Farm, you see that? It burned all the oxidizer out. That's there's still methane in there. This is Central Texas roundabout. Yeah, watch the tower. The tower is a pretty good indicator of what's going on there. Yep, yep, yeah. Yeah. Yeah, that didn't do what you wanted it to do. Okay. Yeah, definitely seeing some green there. Yeah. So, guys, I can tell you that that's the nozzle. The nozzle started doing some weird stuff. I also love that SpaceX has no care about just destroying these engines, one after the other. No, it was going for a second, Rocket, here. Watch. It was going for a second. They got it up to pressure. It's a good start. Good start. And then look, and they shut it off. They concluded that test pretty quick. Whatever that test did not, yeah. Yeah, that's Raptor. That's a Raptor test stand. Yep. Yeah, they got a purge flame on. It's definitely, oh, yep. They vented down that pretty quick. They depressurized that pretty freaking fast, man. That one looks good. Yeah, that looks great. That sounded right. It honked. When it honks, that's... Moo. Depends on what failed, goalie. Yep, those are definitely cows. Definitely some cattle right there. Yeah! That would be me. Shutdown looked okay. I mean, goalie, if this was me, all right, if this was me and we're conducting a test and an engine failed, I would not try to reuse that engine right away. What I'd do is I'd find the part that failed, take it off, and then send it back to SpaceX HQ so the engineers can see it. That's what I would do. I mean, you're going to do rapid testing like this. You got to figure out why stuff failed, or have an FEA, like, materials team at McGregor to basically be able to take these parts off and communicate what happened to them. Yeah, because SpaceX isn't trying to predict the failure. SpaceX is it's not like kind of run-of-the-mill aerospace where you put it on the test stand and if you're going to push it to failure, you expect it to fail at this point. SpaceX just puts it on the test stand, changes a couple of variables around, hits the go button, and whenever it blows up is a new failure mode that you found. They're quite literally doing the Edison light bulb method, but with rocket engines. Yeah, it's pretty much that. Yeah, pretty much that. That's why when if the Raptors graduate through the school of hard knocks, so to speak, and they finally make it on Starship, they work. They work just fine. It sounds expensive. Yeah, Iron, I'm not going to sit here and pretend like it's not, but also Elon Musk has enough money. That's fine. I mean, I don't mean to put it like that, but I'm pretty sure they can handle it. And every Raptor that they make, every Raptor that rolls off of the assembly line, so to speak, it gets cheaper. Your testing gets cheaper because you're mass producing them. That's more data. And more data is equity in the company in this particular case. So Don't think about like voiding these rocket engines as a write-off. Every one of these rocket engines, every one of these Raptors that gets blown away, it would be like adding a new office building to your headquarters. You know what I mean? Or like if you own a shop, having another garage, or if you're a YouTuber, buying a racetrack. It worked. It's a good idea. He did it, and it was awesome, right? That's how SpaceX looks at it. They're not afraid to fail. They're not afraid to fail publicly. But that's fine. If it does fail, you figure out why it failed and you move on. And that understanding is really what that's equity. It's equity in your company. Your company gets more valuable every time a rocket engine blows up. I know it doesn't seem right, but that's pretty much what's going on. I would assume this is faster than other ways of testing. Iron, this is way faster than other ways of testing. Other ways of testing are less expensive. This way is the most expensive, but this way yields the most amount of data. Interestingly enough. Like, it's a nice steady stream of data. I haven't seen any info on it lately, but they were building a new engine production facility at McGregor. Yep. The RVIC they swapped out in S24 the other day had SN115 on it, if I recall. They have a pretty high production rate. No one. Darius, there have been more Falcon 9 engines. There have been more Merlin 1Ds produced in like the past 5 years than pretty much every other rocket engine combined over the past 5 years, like by a long shot. Yeah. Free range beef exposed to SpaceX Raptors written on labels. I hope nobody's trying to make veal, because if they're trying to make veal, then you're gonna have a really bad problem here. But it's very clear that they don't care no more. Yep, it made the honk. There was some residual pop there, but it made the honk. That guy's cool. He also drives a Ford. That's a dang old Ford Ranger. That's a dang nice quarter-ton truck, boy. Ford. Oh. 257-second Merlin test. Hold on. 257 seconds is... Whoa. 4-minute Merlin burn. I know what they're testing. Anybody? Why would they be testing a Merlin for 4 minutes? Anyone? Who knows? This is a really easy one. That heavy. Yeah, it's got to be center core. It's got to be a center core rocket guy. Heavy center core. Yep. TLI burn? Nope. Falcon heavy center core, dude. Has to be. Yeah, expendable Falcon heavy center core. Good job, guys. Hell yeah. I want to see that. Yeah, baby. That guy just casually driving by. SpaceX is way behind on their Falcon Heavies. Rocket Guy, are they? I've heard that there's like 3 Falcon Heavies sitting at the Cape ready to go. It's the payloads that they're waiting on, like SF-44, Peregrine Land? No, not Peregrine. Whatever lander, they're waiting on it. Dude, that's insane. Wow, that's just damn impressive. What would the burn duration for a Falcon translunar injection be? I have no idea. Man. Rocket, that's pretty impressive, dude. 418 from an engine that was really never designed to do that. That's pretty damn good. I don't think it was ever Merlin. I don't think Tom Mueller, when he designed this thing, really anticipated it firing for almost 4 minutes 20 seconds. pretty cool. Payloads are behind, yes. I meant in comparison to their projections. They started in their 2019 projections to ramp it up to 10 Falcon Heavy flights by this year. Or maybe it is by next year, but regardless, the projections are off. Yeah, that's right. I mean, those Falcon Heavies that are sitting at the Capes certainly aren't making them any money, that's for sure, huh? More booms here if you're interested. I think we saw this one, but yeah, let's see. Oh, green. Yep. Green. Not good. Oh, more green. Nope, still bad. Yep, that's the same test though, so it's okay. But also, green. That's the green. When you see green like that, guys, that means the engine's getting too hot. The engine got too hot. That sounded expensive. I'm in danger. But actually, it's interesting to note. It's interesting to note, fellas. Take a hold on. Take a look. Watch. Okay. So watch the flames. Now, don't get me wrong. There is no connection between the BE-3 and the Raptor. They're completely different cycles, completely different engines, completely different propellants. However, if you look at this really slowly, you can see there's something perturbing the flames coming out of the rocket engine. The gases are getting knocked around by something. See how it's inconsistent? See how it's inconsistent and it's light and dark in certain places? Yeah, that's not good. That's not ideal. See that? See that flash right there? Back it up a little bit. Yeah, you see that? No. If a rocket engine is working nice and healthy, the flames coming out of it should be nice and uniform. You might see some residual sparks here and there, but the plume coming out of it should be really, really defined. Perturbing my shock diamonds. That's right. I mean, don't get me wrong. It kind of depends on what type of combustion you're using. Well, yeah, what type of combustion you're using, etc., etc. But in this particular case of Raptor, this should be nice and defined like that, and it should stay like that. And it's definitely not staying like that. Yep. See, more stuff going on right there. Yep. Oh, yep. That's bits of the engine coming out. Yep. Yeah. How much of it is atmospheric distortion? Atmospheric distortion distorting color? I don't know. I mean, I don't think atmospheric distortion is going to make the flames change color. You know what I'm saying? Could be wrong though. That was the loss in oxidizer pressure, Cool Frog. The motor went green, which means it's getting too hot. So I mean, I don't know. It could be just be that the cooling channels failed. But when you see green, that means the rocket engine is too hot and it's burning itself from the inside out. That turns Raptor, the inside of the lining on the nozzle, into an ablative substance, meaning that heat has to go somewhere. So instead of exchanging heat with the propellants like what it's supposed to, it's exchanging heat with the metal that holds the propellants inside. That doesn't, yeah. You basically made a nice ablative nozzle, and Raptor isn't designed to be an ablative nozzle. With that being said, there are rocket engines that are designed to have ablative nozzles. That's fine. Falcon 9's second stage, the Merlin 1D vac, has an ablative nozzle because it's only designed to be used once, or twice, or 3, or 4, or 5 times, like what we saw the other day. That was a great mission, by the way. Raptor 144 on the tripod. Jeez. Oh! Oh! Yeah, that's... That... Yep. Sounds like another hard start. Let me hear it. Pop goes the Raptor. Okay, let's listen. Nope. Nope. That's not a hard start. It got up, it got going, then it didn't get going. Oh, that's that'd be pretty good, Aqualex, yeah. Oh! Man. I need to get a drink. I'll be right back. Watch the rest of this video. On throat. Got my liter of cola. Ooh.
Discovery, go at throttle up.
Gold Falcon, 27 months. Oh. Bottle rockets. Yep, that didn't work. Hey, Jado. Yeah, that didn't work. That looked like a nitrogen. That's the old super heavy LOX header tank. Oh. Yeah, that didn't work very well, did it? Anyway, cool footage of... I mean, it's pretty cool footage seeing all that stuff, dudes. You know, not all the time that you get to see the rocket engines kind of voiding themselves. It's really cool. You learn a lot about propulsion and how it works and how... I mean, rocket guy, you tell me. It's a balancing act, man. Everything has to go right. You have to get all the pressures right, and they have to be right in the right sequence. And they have... Yeah, or else... Yeah. Or else, well, something pops. Huge tan ball. What's that? It's a space hab module. Waiting for SpaceX to make how not to make a rocket engine video. Dude, if we could see some close-ups of the plumbing failing rocket guy, that would be pretty cool. That would be pretty awesome footage. Looking at this makes the desire to remove flanges more understandable. Can't blow a head gasket when you don't have one. Best part is no part, right? Best be hiring a lot of TIG welders. Of course, believe it or not, from our auction soiree yesterday, or Saturday, believe it or not, yeah, it's not, ITAR isn't as bad as you might think, as long as the rocket engine is assembled. It's the pieces inside. It's the pieces inside that they really don't like. So, yeah, you know, seeing them up close is not a problem, which is interesting. Okay, what else do we have from NSF here? How soon? All right.
This video was
Okay, we got Jack Byer here. Let's see. This video was sponsored by...
Brilliant.
Sponsored by Jack.
How long will it be until Starship launches from Florida? Perhaps we can come up with an estimate based on the progress we've seen at the Cape, plus what we witnessed in Boca Chica. In this Cape flyover, the Florida Starship factory has progressed lightning fast, no 4 towers needed, and the Starship launch tower at 39A is almost complete. Meanwhile, SLS is still on the pad, but maybe not for long. All that and more starting right now. Beginning, as always, with SpaceX's Roberts Road facility, we can see major progress on the Starship factory, or Star Factory, building. When you take into account how it looked on our last flyover, the rapid pace is clear. The first portion of the building already has a roof in place, and an exterior wall has gone up as well. At the same time, more framing has gone up for the second part of the factory.
Also, they're continuing to stage prefabricated roof sections in an assembly line-like fashion.
This is looking more and more similar to the equivalent building over at Boca Chica. To the east of the factory building, we can see progress on the Cape's future Mega Bay. One of the smaller cranes at the site is now situated at the center of the impending structure, and SpaceX's own LR-11000 crane is standing by outside waiting for major construction to begin. Meanwhile...
Oh yeah, they bought another one of those, by the way.
More and more parts are being staged nearby.
No.
Based on how long it took them to build the Mega Bay at Starbase, we can expect this structure to be done in around 8 or 9 months. Starbase Mega Bay was begun around the end of August 2021, for reference. So a year from now, the Cape Mega Bay could very well be operational. Near the entrance to the Mega Bay, a set of smaller foundations have been laid. This is similar to how the High Bay and Mega Bay were built at Starbase, with a set of smaller foundations to one side of each building, where each level was prefabricated ahead of being lifted and installed on the structure. Over to the northern fabrication area, progress continues on the chopsticks, their carriage, and the ship quick disconnect arm. The chopstick arms themselves can be seen with the rails already installed. These will be needed in order to stack and catch boosters at the pad once SpaceX is ready to do so.
That's cool.
A crane can be seen holding the shoulder section of the QD arm. This is the part of the arm that will be closest to the Starship launch tower. On the carriage system, a hydraulic accumulator has been installed, which will aid in the opening and closing of the chopsticks during their operation. Before a Starship can launch from Florida, all of these pieces must be finished and transported to 39A, then assembled on the tower, of course.
Yeah, okay, I just want to say this real quick. I don't really like pausing the video too much. This video that came out from NASA Spaceflight in the last couple of days is already outdated. It's already outdated. Crazy.
Based on the same activities in Boca Chica, we can expect this to take roughly 4 or 5...
Who does SpaceX contract for the chopsticks? STI Mechanical Construction and Fabrication. That's my guess.
To the Starship launch tower. On the carriage system, a hydraulic accumulator has been installed, which will aid in the opening and closing of the chopsticks during their operation.
Friends of
Before
yours,
a Starship can launch from Florida, all of these pieces must be finished and transported to 39A, then assembled on the tower, of course. Based on the same activities in Boca Chica, we can expect this to take roughly 4 or 5 months. Over at the tower construction area, you can see the final tower segment with the chopstick pulley system already installed, with a set of self-propelled modular transporters underneath.
Gone.
This indicates that at the time of the flyover, rollout for this segment was imminent.
Sure enough, just after our flight, the final tower segment rolled to 39A.
See what I mean?
It may have even been stacked on the tower by the time you watch this. Once this has happened, the Starship launch tower at pad 39A will be at its final height.
Speaking of the 39A launch tower, let's jump on over to Launch Complex 39A because the Starship launch tower
is, in fact, 3 levels higher than our last flyover.
What the
Although
hell?
in this shot, it's only 2 levels higher, because segment 8 was lifted after we flew.
At this point, it dwarfs the fixed service structure for Falcon 9. Progress continues, as always, on the ground systems needed to support Starship testing and launches at 39A. The big cryogenic tank at 39A is now at least twice as tall as it was on our last flyover, and construction of another tank has begun to the north. This newer tank appears to use more of a traditional construction method. Given its placement, it wouldn't surprise me if this was additional methane capacity, but we'll just have to wait and see. Moving on to the south of this tank, the newly refurbished hydrogen-turned-methane sphere is all white and shiny now compared to our last flyover, a good sign that its refurbishment is done. Additionally, a new set of transfer lines can be seen, going from the methane tank farm all the way to the south where the launch tower is located. A better vantage point to see all of this was recently facilitated by our good buddy Harry Stranger, who recently updated us with imagery from satellite views of 39A, and we can see all of this progress from an orbital perspective. We can spot the new subcoolers that have been added near the large cryo tank. adding some weight to the hypothesis that it will be part of the LOX tank farm for Starship. On top of this, it should be noted that the LOX sphere that SpaceX currently uses at 39A for Falcon 9 and Falcon Heavy launches has not seen any work at all in the past month. There also seems to be another addition to the tank farm that is similar to what has been built in Boca Chica, a cryogenics bunker. This will house all the vital components needed to control and distribute the propellants and other necessary commodities into the tower and orbital launch mount to feed both ship and booster during tests and launches. Both in these satellite views and in our own imagery from the flyover, we can see that the strange hexagonal structure at the old Starship landing zone has had pipes and other structures added to it, deepening the mystery as to what it will be used for. Based on all of this, I'm guessing, and I want to be clear that this is a total guess, that we're around a year away from seeing a Florida Starship launch, at least. And that timeline might need to involve a vehicle that wasn't built at the Cape. No, I don't think they'll fly ships or boosters to the Cape from Boca Chica, as cool as that would be. Instead, I'm referencing repeated rumblings we've heard of ships and boosters being transported to the Cape from Boca Chica via barge. What do you think? Is that too long, too short, or just right? Let us know what you think in the comments. That's not all for 39A though, as on the main ramp, the Falcon 9 TE, or Transporter Erector, is missing, indicating that it has been rolled back to the horizontal integration facility for rocket integration and launch. What are they launching this time? You guessed it, it's another Starlink launch!
Update. Booster 1058 flew a record 14th flight, deploying its Starlink and other payloads, and then succeeding in sticking to 14th landing. Amazing.
I can't believe I was at the Cape for 2 weeks and saw 2 Starlink missions but not SLS launching. What's that? Who said that? Not me. Orange Rocket good! Speaking of Orange Rocket, at Launch Complex 39B, SLS remains on the pad after its 2 scrubbed launch attempts.
How dare you!
The plan is currently to try and fix the liquid hydrogen seals that leaked on the second launch attempt at the pad, rather than roll the entire vehicle back, since that lets them test the fixes with cryogenic liquids and temperatures. NASA has set a launch date no earlier than September 23rd, pending a successful wet dress rehearsal on the 17th and the range extending the certification time on the flight termination system batteries. However, if they don't get that extension, or if further issues pop up, then a rollback will be needed and the launch date will slip further. Speaking of SLS, we do have SLS merch. The Exploded View t-shirt comes in 2 flavors, one for fun and one for fans. The fun one will help you chuckle, and the fan one will help you remember every part of SLS before the next launch attempt. Over at Slick 37B, no rocket is visible. What is cool to know though is the fact that the hydrogen stored at this pad can also be used to assist SLS.
Yep.
If they need to fast replenish the hydrogen storage at pad 39B, they can use the facilities at 37B for that. Neat! Next up, let's move over to Blue Origin's Exploration Park campus. Work on the warehouse expansion continues. No, for real, construction on the frame of the warehouse expansion has begun, and at the same time, a large number of parts are being staged nearby. Next to the warehouse, a larger area has been cleared, and new plans show this to be for a composite assembly building and a reef pathfinder building, also a vertical assembly area. It's likely this area will continue to grow with even more production buildings over time to support Blue's future plans. Let's hope we see serious foundation work in the area by our next flyover. Over at the Toucat, the building received some blue siding, making it look more like the rest of the facility. The work on the roof is finished and a path is being prepared in front of it. Work also appears to be continuing on the inside of the Toucat, which will host future New Glenn second stages for cleaning and testing, hence the name Toucat. Meanwhile, over at Blue Origin's Launch Complex 36, we can see that the second stage test tank is no longer on the stand at the north end of the complex. This could be a sign that the testing of the tank has been completed, or maybe the tank is back inside and being worked on before another round of testing. On the eastern side of the pad, behind the water tower from this perspective, there are new foundations being prepared. Site revision plans from March label this as, quote, GS1 test area. We have seen Blue Origin use GS1 as a designation for Glenn Stage 1 before, so it seems that this area will be for testing New Glenn first stages. Next up, over at Relativity's Launch Complex 16, Terran 1 is still testing outside, ahead of its launch attempt in the near future. No second stage is visible yet, which will of course be needed for the orbital flight test. We'll have to keep our eyes and ears open and see when Relativity will announce a more firm launch target for its rocket. Meanwhile, over at the port, both drone ships were at sea during this flyover, though Just Read the Instructions was a few hours from returning with Falcon 9 Booster 1052. Luckily, it was visible returning on FleetCam, our 24/7 live camera in Port Canaveral. It's still crazy to me that SpaceX can just routinely land 20-story rockets on barges out in the middle of the ocean.
I agree.
If you want a better handle on some of the mathematics involved in such an amazing feat of engineering, check out our sponsor for this video, Brilliant.org.
So, Jack's not wrong when he says it's like a skyscraper tall. See all this right here? You see that right there? This little hatch? That's a door. So that means a person is about the size of my mouse cursor. Yeah, see that? That's the door. That's a door. That's just a regular human-sized doorway. How many launch complexes are there in the United States? 4, technically 5, if you want to play technicality. Clayton, there's 4. But 5, technically. So, there's Kennedy Space Center. Everybody knows that one. Vandenberg Air Force Base in California. Then there's Mid-Atlantic Regional Spaceport, or MARS for short. That's Wallops Island. And then Kodiak, Alaska. The Air Force actually has a test range up there. And they launch out of Kodiak, Alaska. Those are the 4 main launch sites that the U.S. uses. With that being said, the 5th one, and this is the technicality, that's Starbase. Starbase is the 5th one. But nothing launched from Starbase has ever gotten into orbit, so whether you want to call it a launch site or not, I let's just say 5 with an asterisk next to it and call it a day. A decade ago, would you ever imagine we seen this much activity? No, this is fantastic. How do you feel about spin launch? I mean, armchair, I think it's cool. I think spin launch is cool. I don't necessarily have a problem with it. Dude, it is certainly a way. It is a way to do that. You could get really technical, include quads. Yeah, if you really want it. Yeah, if you really want to get super technical, sure. Yeah. What about Spaceport America? I mean, the gist of what we're talking about here, guys, and let's not get too far into technicality. Orbital launch sites, I think, was the premise of the question. There, in terms of suborbital, there's suborbital launch sites everywhere. They're all over the place. Yeah, Armed, I think spin launch could work. Like, a lot of people hate it. There's a lot of stuff that needs to go right to get that thing to spin correctly. But yeah, I mean, I don't see, there's nothing with practical physics that's saying like it can't work. Of course it could work. Yeah, there's nothing saying that that couldn't be done. Oh, there's your scale. Oh, nice, goalie. Well, the rocket doesn't weigh much, Flykin, so it's really easy to compensate. Anyway, here's our list of upcoming missions here. We have a Falcon in about 4 hours. We're inside of 4 hours here. We got a Starlink, and then tomorrow, basically right to start off Space News, we got the Owl spreads its wings. We got a Rocket Lab launch. On the horizon here, we have the ABL RS-1 demo on the 19th, and Firefly on the 19th at one of those is not gonna be that date. Race to orbit. Also, it's on a Monday. Firefly just really likes scheduling launches on my day off. Yeah, every launch that they've scheduled has been on my day off. And it keeps scrubbing. So maybe you shouldn't do it on Mondays or Sundays. Maybe you shouldn't do that. Maybe it's a sign. Time for some split screen action. Yep. Yeah, unbelievable. Okay. And that's actually going to be it for Space News, dudes. That's all. I don't think we got anything else. Either way, there's a lot of stuff going on, man. There is a lot of stuff going on. Yeah. The market has changed. Yeah, that's right. Tell my flight director to stop playing Galaga? Nah, he's good. I thought Sunday and Tuesday were your days off. Must have changed. It changed like a year ago. So, funny story. I have buddies that run these websites that tell you, when when launches are. So what I did was I had them compile a list over the last couple of years of statistically what days rockets launch on. And